Hello everyone and welcome back to your data science full course. This is part 3 of our comprehensive 50-hour journey to transform you into an advanced data practitioner. In part 2, you have mastered two essential pillars of data science: Python's Pandas library and fundamentals of statistics. If you haven't watched the video yet, click the iCard above. Over the next 10 hours, we will dive deep into the normal distribution, a cornerstone of statistical analysis. First, you will learn the theory and the intuition behind the normal distribution and its key properties. We'll explore why it's so prevalent in natural and social sciences and how it serves as a foundation for inferential statistics. Then we'll cover essential related concepts like central limit theorem, Z-scores, which allow us to standardize data and make powerful statistical inferences. By the end of this part, you will not only understand the normal distribution but also be able to apply it to real world data to make confident, data-driven decisions. So without any further ado, let's dive in. Now let's look at the learning objectives. So by the end of this 10-hour tutorial, you will be able to understand the normal distribution, explain its properties including its shape, symmetry and the role of the mean and standard deviation. Apply the central limit theorem. Describe how it allows us to use the normal distribution to analyze sample means. Conduct basic statistical inference. Use the normal distribution for hypothesis testing and creating confident intervals. Utilize Python for analysis. Apply Python libraries like NumPy and SciPy to work with and visualize normally distributed data. Machine learning isn't just the future, it's the present. Companies worldwide are hiring professionals who can turn data into actionable intelligence. Take your skills further with Liverpool John Moores University's MS in Data Science, powered by upGrad. Learn from world-class faculty, work on industry projects, and receive one-on-one mentorship to accelerate your career. Don't just watch the AI revolution, be the part of it. Click the link below and start building your expertise today.
Hello everyone, this is Sujit Mukhopadhyay again, and I welcome all of you to the second session on statistics. So today we are going to discuss about normal distribution. Normal distribution is one of the most powerful inventions in statistics. Now if we look at the name very closely, we find that it's called normal and then it's a distribution, right? Now why the name normal? Before that, let's briefly understand what is distribution. See, distribution is nothing but a collection of data. It's a collection of data. Now, why normal? Because through normal distribution, we can observe a lot of phenomena which occur in our day-to-day lives, and through normal distribution, we can explain a lot of phenomena. Like for example, if we think about, say, height of 30 students in a class. So now if all these 30 students belong to one class, one section, one city, with all the demographics being similar, we expect that most of them will be having a height which is going to be similar, along with some exceptions. Exceptions will always be there, but most of them will be having very similar kind of height, provided their age, area, nutrition, and everything else is the same. Same goes for weight, same goes for IQ, same goes for income. If we take a homogeneous set, we will expect that most of them are going to have very similar kind of attributes, and there will be some exceptions here and there. So now let's take an example. Suppose we have taken a class test and the scores are out of 5. So we have taken the scores of say 28 students, or actually for the sake of just a whole number, let's make it 30. Say so we have to add two numbers here, 3.23 and 4.88. Perfect. Okay. So now we have taken the scores of 30 students in a class and we want to understand their ratings out of 5. So what we'll do is we'll just put it in a online graph generator and we'll see how the distribution looks like. So for that, what I have done is I have taken all these values and put it as comma separated values. Now I'll just copy this value from here and just then go to an online tool and we'll just perform one test. Do not worry about calculate Shapiro, Wilcoxon, everything. So we'll discuss about that later. Yeah, now it should be fine. So let's do this step by step. So the first thing what we see is that the number of samples are 30 and the mean is 3.174 and the standard deviation is almost 1, 0.99. So now what we'll do is we'll try to observe what kind of data have we got. So here the mean is, as we can see, 3.17 and we can see a lot of values are hovering around the mean. So mean is 3.17 and we can see a heavy distribution of data between mean. What we can also see is that if we take mean and one standard deviation, so the mean is 3.17 and one standard deviation is almost 1. So that means the range will be 2.17 to 4.17. If we just take one standard deviation to the left and right of the mean. So this is the mean. And standard deviation is 1. So if we look at this range, mean minus 1 and mean plus 1. So let's see how that looks like. So what we can see is that a lot of data are hovering between mean and one standard deviation. In fact, mean and one standard deviation will be somewhere around here. So this is 2.17 to 4.17 will be here. So if you look at this area, most of them or most of the students have got a rating between this region, between 2.17 and 4.17. Yes, there are some exceptions here. Yes, some of them have scored very low, some of them have scored very high, but most of them are falling between this range. Okay, we'll look at what other things mean here. We'll look at in a while, but right now what we understand is that if we plot the values against the frequency is how many times have they occurred. So what we get to see is that for a particular data distribution, for a particular column, most of the values hovered between mean and some values of standard deviation. In this case, we can see most of them are being within one standard deviation. However, we'll look at the actual rule in a bit. But what we understand is that between a certain region of mean and some values of standard deviation, that will be 1, 2, and 3, which I will discuss in a bit more detail, we will find that a lot of values are occurring. So now let's understand what are those ranges. But before that, why normal distribution is so powerful? Because through normal distribution, we can explain a lot of natural phenomena. Think about age, height, weight, income, IQ, and so on. So a lot of natural phenomena can be explained through normal distribution. We will find that if we use normal distribution, rather if we analyze the data of these phenomena between a homogeneous set, we will find that most of them will follow a normal distribution. Now, how a normal distribution looks like on a high level, it looks something like this, where there is heavy concentration of data around the center and its suburbs. These suburbs will explain with standard deviation in a while. So between mean and some level of standard deviation, we'll find that most of the values are occurring. So what is the exact rule? So what normal distribution says, suppose this is a normal distribution. So as we have seen in the last class, suppose this is my midpoint or this is my mu. Say in this case my mu is 50 and my standard deviation is 5. So suppose if this is mu, if this is 50, so let's make it 50. So what I'm doing is I'm marking the regions with respect to standard deviation. So if this is mean and this is my standard deviation, then this is 50, which is my mean, and then I have gone to 1 standard deviation, 2 standard deviation, 3 standard deviation on the right hand side of the mean, and then similarly 1 standard deviation, 2 standard deviation, and 3 standard deviation on the left hand side of the mean. Now, in order for a distribution to be called normal, the rule is that between mean and one standard deviation on both left and right side of the mean, we will have 34.1% of the data. So each side is going to have 34.1% of the data. Now what that means? So if we can see that in this case, if this particular distribution is a normal distribution, we assume that this is a normal distribution, then if the mean is 50 and standard deviation is 5, then what we shall observe that if the distribution is normal, in that case between 50 and 55 we will observe 34.1% of the data. Similarly, between 45 and 50 we'll observe 34.1% of the data. Similarly, between 1 and 2 standard deviation, which is 40 to 45 and 55 to 60. $13.6 each. Let's actually use a different ink. So between 1 and 2 standard deviations, so this is 3 sigma, this is 2 sigma, this is 1 sigma minus, this is my mean, this is 1 sigma, 2 sigma and 3 sigma. So now what we get to see is between 1 sigma and 2 sigma we get around 13.6% of the data. Between mean and 1 sigma we get 34.1% of the data, and also on the negative side. So now if I have to look at, if I have to take all these and say look at this particular range, which is mean plus minus 2 sigma, that is 40 to 60. Between this, if we add this up, we should get 95.4% of the data, which means between mean and 2 sigma on the left and right side of the mean, we should get around 95.4% of the data. Now let's see what happens between mean and 3 sigma. So before that, we'll look at what happens between 2 sigma and 3 sigma. This is 2.1%. This is 2.1%. The color is not very bright, but I just wanted to distinguish between the colors. So now, if I take this and go from 35 to 65, which is mean plus minus 3 sigma, will end up seeing 99.6% of the data. How do we get 99.6? We add this, add this, add this, add this, this, and this. So if you add 1, 2, 3, 4, 5, and 6, you add 1, 2, 3, 4, 5, 6, you should get 99.6% of the data. So what that means, that in a distribution which is normal, 99.6% of the data falls between mu and plus minus 3 sigma. Now what happens with the values which are outside this range? Very simple, we call it as an outlier, or in some cases we call them as extreme values. Generally we assume that any value falling between mean plus minus 2 sigma is normal. Outside that we call it as an outlier. Between 2 sigma and 3 sigma we call them as outliers. Outside 3 sigma, extreme values. Extreme values are values which are even higher than outliers, right? So let's do a small exercise and understand how normal distribution works. One simple exercise will really help us. So what we'll do is, let's come here. Suppose we take a problem where we are looking at how many runs Virat Kohli is going to score in the next match. So I ask you, hey, can you make a guess? Can you make a guess at how many runs Virat Kohli is going to score in the next match? You say, how do I know that? Okay, I will help you. I'll give you some hints. What is the hint? I'll tell you that his average is 60. His standard deviation is 5. And his scores follow a normal distribution. If his scores does not follow a normal distribution, then it becomes a different thing. But right now we'll not bother about it. So if I tell you these three information, can you try to predict how much he's going to score in the next match? So let's try. So what we know is that between mean and plus minus 1 sigma, we get 34.1% of the data. Actually, I should say it should be actually 68.2 because 34.1 on one side. So on both the sides it's 68.2. So between mean plus minus 1 sigma to mu plus minus 2 sigma, we get 13.6 into 2, which is 27.2, and between mu plus minus 2 sigma and mu plus minus 3 sigma, we get 2.1 into 2, that is 4.2%. Now let's take these things and try to make a guess. So what we can say, I can say is that, okay, I am 34.1% confident that he will score between 60 and 65. I am also 34.1% confident that he will score between 55 and 60. So this is mu plus 1 sigma. This is mu minus 1 sigma. So mu minus 1 sigma and mu plus 1 sigma. If we take this range, we can see that we can predict his score with 34.1% confidence. Now, if we take both of these things together, and we look at this range, we can say that he will score between this range, and I am around 68.2% confident about it. So now we can see just with these three information how easily we can make predictions. If we go even further left and right, say I'll go maybe one more standard deviation to the left and one more standard deviation to the right. This range, one more standard deviation to the left and one more standard deviation to the right, which is mu plus 2 sigma, mu minus 2 sigma. I am 95.4% confident that he will score between this range. If I go even further, this becomes slightly clumsy. So let's just make the 5 a bit look good. Yeah. So between mu plus minus 3 sigma, I can predict with around 99.6% confidence. So I can say, hey, you know what? I am 99.6% confident that he will score between 45 and 75. So if anyone asks you, what are the chances that he will score, say, between 60 to 65, you can say 34.1%. What are the chances that he will score between, say, 55 and 65? 68.2%. What are the chances that he will score greater than 50, or he will score at least a 50? We'll say 95.4% chance, provided he scores follow a normal distribution. So now we can see that using normal distribution and just knowing the mean and standard deviation, we can make super powerful predictions. and that is the power of normal distribution. So now we can know that normal distribution can be applied to a lot of natural phenomena. And if we just know the mean standard deviation and know that the data distribution follows a normal distribution, we can make a lot of predictions. That's the power of normal distribution. Now, how can we generate a normal distribution? So this is a small utility which you can use. If you go to this website, and there's a lot of other websites as well, you can just say, hey, you know what? Say my mean is 5, my standard deviation is 2, and say I want to create a data set for 50. So now we can see that we have got a data set which is normally distributed, having a mean and standard deviation of 2 and 50. Mean of 2 and standard deviation, sorry, mean of 5 and standard deviation of 2. Okay, so through a lot of utilities, if we just mention the mean, standard deviation, and what is the number of observations in my data set, we can generate normal distribution. Now we'll look at a concept called Z-score. Now what is a Z-score? So Z-score is represented as a number which says how much standard deviation a particular point is away from the mean. Sounds very confusing, but it's not. It's very simple. I'll just show you in a moment. So suppose I have a distribution which is a normal distribution. See, this is the mean. Suppose this is one standard deviation, two standard deviations. So suppose this is the mean is 60 and standard deviation is 5. So now if you look at it intuitively, how many standard deviations is 65 away from 60? The answer is 1. If you look at it intuitively. Now let's calculate it mathematically. So as I said, Z-score is how many standard deviation a particular data point is away from the mean. So the generic formula is x minus mu by sigma. So here, this is my x. So now we can see that the Z-score of 65 is 1. So 65 minus the mean, which is 60, divided by standard deviation is 5, and we get 1. So now suppose we want to calculate the z-score of, say, this point. Say this is 67, for example. Suppose this is 67. I want to know how many standard deviation is 67 away from the mean. So this will be 67 minus 60 divided by 5. So 7 by 5 should be 1.4. Yeah. So 67 is 1.4 standard deviations away from the mean. So you must be wondering, why is this required? We'll look at the applications of these things in the later videos. But right now, let's understand this concept of z-score, because understanding z-score, understanding normal distribution will help us solve a lot of problems. So now what we will do is, we'll look at few other variations. We'll look at what is the right skew distribution, what is the left skew distribution, and we'll also look at how to convert a non-normal distribution into a normal distribution. Before that, so far you have looked at the normal distribution. Now this normal distribution is also called, yes, you guessed it right, the famous bell curve. Now you must be wondering, oh, is it the same bell curve which we used to hear in our appraisal discussions, where our manager used to say, hey, you know what, I gave you 5 rating, but there's some HR who did some bell curve and you couldn't, we were not able to fit you into the bell curve, and that's why we had to lower your rating. I'm sure we have heard this kind of discussions. And if you're a manager, I'm sure even you have had this kind of discussions with your reportees. So yes, normal distribution is nothing but the bell curve. Why? Because if you look at the distribution, it takes the shape of a bell. So normal distribution and bell curve are one and the same thing. And it is this bell curve who is the culprit behind our lower ratings in the appraisal. Jokes apart, we'll now look at right skewed and left skewed distribution. So first we'll look at a right skewed distribution. So a right skewed distribution looks something like this. As you can see, this is not a normal distribution. This is a right skewed distribution. And we'll look at another distribution. This is my midpoint. So this is the left skewed distribution. What that means? Now, if we plot our data, at times we may see that the data may follow this kind of perfect normal distribution, or it can follow this kind of distribution as well. or it can follow this kind of distribution as well. It's not necessary that it has to be a normal distribution always. If the distribution looks like this, it's called a right skewed distribution. If the distribution looks like this, it's called a left skewed distribution. Now, what are the properties of a right skewed distribution? In a right skewed distribution, the mean is always greater than the median. In a left skewed distribution, the median is greater than the mean. In a normal distribution, the mean and the median will almost be equal. It's not 100% equal, but it's like almost equal. So in a right skewed distribution, we see a long tail along the right. In the left skewed distribution, we see a long tail along the left hand side of the distribution. Now what this means? This clearly means that on the right hand side of the mean in a right skewed distribution, we have less values or few values. On the right hand side of the mean, if this is the mean, the right hand side of the mean, we will find less values. On a left skewed distribution, on the left hand side of the mean, actually this is not looking very good. It should actually look like this. So on the left hand side of the distribution for mean, we'll have less values when it comes to a left skewed distribution. My left skewed distribution is not looking very good, but let me just try to make it look good. Yeah. So we'll have less values on the left hand side of the left skewed distribution. How do you remember what is right skewed, what is left skewed? Through a very simple formula. Just memorize this. Skew is few, which means the side of the mean where we have less values, we call that distribution accordingly. So in this distribution, we have few values on the right side of the mean. So going by this formula, we call it as a right skewed distribution. Here we have less values on the left hand side of the mean. So going by this formula of skew is few, we call this as a left skewed distribution. Now let's look at some of the properties of a right skewed and the left skewed distribution. So how do we calculate skewness? So we can calculate skewness by taking the mean of the distribution, then subtracting each observation from the mean, then taking it to the power of cube, summing them up, divided by n is the total number of observations and sigma is the standard deviation. So this is each observation. This is the mean. Number of samples or number of data points whatever you want to say, and this is my standard deviation. So using this formula we can calculate skewness. If the skewness is negative, we call it as a left skewed distribution. If the skewness comes to be positive, we call it as a right skewed distribution. If the skewness is closer to 0, that's a normal distribution. So now we'll just look at it. So I have few data sets here. This is the first data set. So this is the first data set. And as we can clearly see that on the left hand side, we have less data point. So intuitively, we know that it's a left skewed distribution. So now we'll calculate skewness. How? We'll take each observation. So if you just look at what I have done, I have calculated the mean. Then from each observation, I have subtracted the mean, and then I have taken the cube of it. So which is basically I'm calculating the numerator part for all the observations. So for each observation, as you can see, this minus this raised to the power of 3, and I have kept on doing it, and then I have just added them up, which is this summation. So that takes care of the numerator. Now I'll calculate the standard deviation. So I've used the standard formula of Excel, and I've calculated the standard deviation. Now I'll calculate the denominator. Denominator is n minus 1 into sigma cube. So n is the number of observations minus 1. So as you can see, this is n minus 1, and then I have taken the standard deviation and then raised it to the power of 3 and then multiplied both of them. So that gives me my denominator. Now my numerator by denominator gives me the skewness. And as we can see here, this is negatively skewed. And I had said that in a negative skewed distribution or a left skewed distribution, so left skewed distribution is also called a negatively skewed distribution, and the right skewed is called a positively skewed distribution. So in a negatively skewed distribution, I had said that the median is greater than the mean. So let's look at it. So median is greater than the mean. Similarly, if you look at these data points, there are fewer data on the right. So if we do the same calculation, we find a positive skewness. And here, mean is greater than median, which I had said for a right skewed distribution, mean greater than median, which we can clearly see here. Now the third one is a normal distribution, more or less normal. And in this case, we can get to see that the mean and median are close, number one, and the skewness is very, very close to 0. And just by the looks of it, it looks like a normal distribution. Now the point is, how do I actually say whether the distribution is normal or not? So this can be done using 3 techniques. Let's look at the first technique. This is a manual technique. So here, as you can see, I have weight of apples in grams. I have weights of apples in grams. Now I want to know if this is normally distributed or not. Yes, I can look at I can plot the frequency, and intuitively I can say, but that is not good enough. I have to mathematically prove it whether this is normally distributed or not. So let's take a crude manual method. It is not foolproof, but at least it will give you an idea. So here, what I have done is, I have taken all the entire data here and just sorted it in ascending order. After that, I have calculated the mean, as you can see, and the standard deviation. Now I have total 55 observations. So going by the range, you remember between 68.2%, we should, or rather between mean plus minus 1 standard deviation, we should get 68.2% observations. So in this case, I have taken mean minus 1 standard deviation and mean plus 1 standard deviation. That should contain 68% of the data, which means I expect around 37 observations or 37.5 observations between this range. In our case, we found that there are 32 such observations between 13.53 to 20.97. So 13.53 starts from here, and if we go to 20.97, that will be up to here. So we get around 35 observations. Our expectation was 37. So it does not meet the exact requirement, but it's close. Between 95.4%, that is between 9.81 and 24.69. Our expectation is 52.25. Let's see how much is the actual. So 9.81, which means it starts from here to 24.69, which literally comes everything. So our expectation was 52, we got 54. And the third case, it's obvious that between 6.09 and 28.5, 28.41, our expectation is 54.78, and we get all the observations. So now, can I call it as a normal distribution? On a high level, looking at it, yes, more or less. But there are better ways of calculating this. So now we'll calculate using a test which we called as a Shapiro test. So there are a lot of online calculators where we can do this test. So just copy paste these values and calculate this test. So right now, you just remember one thing. We get two values, W calculated and W critical. Do not worry how they came, what are those, don't worry about them. Actually, W critical is this one. So I'll give you a quick hack which you can memorize, and then later we'll understand what these things are when we'll look at hypothesis testing. Now just remember a very simple formula. And the formula is, if W cal is greater than the critical value, actually this was right. So ignore this. So if calculated value is greater than the critical value, then the distribution is normal. So W cal, or this value, if I call this as W cal, and if I call this as W crit, Right now, just remember that if this value is greater than W crit, then we can say that the distribution is normal. It's a normal distribution. How did they came? What is this p value and all this? Don't worry about it right now. We'll understand these things in bit more detail when we study hypothesis testing. But right now, just remember this simple hack. You just take your data, put it in any kind of calculator. There are a lot of online calculators, and if you are doing a Shapiro test, the thumb rule is if WCal is greater than W crit, calculated value is greater than the critical value, then we can call that the distribution is normal in nature. If that is not the case, then we say that it is not normal. If WCal is less than W crit, then we can say that this is not a normal distribution. So just remember this hack for the time moment. So now let's look at one more way of checking, and that is called QQ plot. So a QQ plot basically looks something like this. A normal distribution, a QQ plot looks something like this. This is a QQ plot, and if the distribution is normal, most of these points will be very close to this red line. If that is the case, then we can call that the distribution is normal. Okay, here we can say we can say that this is somewhat normal. It looks somewhat normal, not exactly, but somewhat normal. And then, in order to be 100% sure, you can look at a Shapiro test. So now what we'll do is we'll just look at how a left skewed and right skewed distribution looks like, how their QQ plot looks like, and we'll also look at if is it possible to convert a left skewed or a right skewed distribution into a normal distribution. Is it possible or not? So I am coding it in Python. Even if you do not understand Python, that's fine, as long as you understand the essence. So I have a file which I have named as normal distribution.xlxx. So here I have got 3 tabs which I have named as left skewed, right skewed, and normal. So I have parsed this left skewed here in a data frame. Similarly, I'll do it for a right skewed distribution and a normal distribution. Then I'll merge them and put it in a single data frame. So I have left skewed, right skewed, and normal distribution. Perfect. Now what I'll do is I'll try to create a plot. So this is the code which we can use to draw a QQ plot. It will take the data frame and the variable. So for the left skewed data, I am passing the data frame and the variable, and let's see how the data looks like. As you can see, a lot of points are not really on the line, and even if you see here, we can see that in the left hand side there are less data. So you remember skew is few, in the left side there are less data, and here also we can see that a lot of points are not on the line. Similarly for the right skew data, here we can see there are less data points on the right, and the same goes for the QQ plot. We can see that a lot of points are not on the line or not even close. What about the normal distribution? Here this is somewhat better. Most of these, apart from that, these 2-3 odd points here and there. So if I just ignore these two and these points, we can see most of the points are very close to the line. Now what I'll try to do is I'll try to take the left skew distribution and see if that can be converted to a normal distribution or not, or at least bring closer. So what I have done is I'm applying logarithm on the entire distribution. So I take a log of the entire data set, and I'll try to see if the left skew distribution can be somewhat made normal. So after doing this, I can see, yes, some improvement has occurred, but not something very drastic. Now what I'll do is I'll use a reciprocal transformation. So now what I'll do is I'll use a reciprocal transformation, and the reciprocal transformation, what we'll get to see is that I do a 1 by all the observations. So if I do this, so I take each observation and I just make it 1 by that particular observation. It still does not look very good with reciprocal. Now what we can do is we can do a square root. So this is a square root of transformation method. So after I have taken square root, as you can see, it's exponent to the power half. Still does not, I mean, yeah, it actually there's some improvement has happened. It's much better than previous. Now what we can do is we can do an exponential transformation. I can raise each observation to the power, to a high power. And this is much better. So we can see that for these particular data points, if we apply an exponential transformation, that is we raise each data point to the power of 4, by the way you can keep on varying it, we see that we have been able to bring it closer to a normal distribution. There is also one very popular method called Boxcox Transformation. This one also brings the data points very close to being a normal distribution. So now let's just look at the original data distribution which was there. This was the original. Now if you compare it with the Boxcox or an exponential transformation, we see a much better result. However, For each data set, you can keep on trying all these methods and see which one is coming closer. So intuitively we can see that for this particular observation or particular these data points, exponential transformation and Boxcox transformation have performed much better. So now let's look at the entire data frame. So what we did was, this is my original data and I have tried to convert it into reciprocal, square root, exponential and Boxcox and logarithm also. So we can see that we have tried to do all this stuff, and in reciprocal I have done this as like 1/7. Square root, I have taken square root of this, right? For exponential, this has been raised to the power of 4. And then Boxcox is a special transformation, which I am not going to the details of Boxcox as it's out of the scope for this particular video. But for your knowledge, you can just know that it's a very powerful way of converting a non-normal distribution into a normal distribution. So having said that, I think we covered a lot of ground with respect to normal distribution. We understood what is a normal distribution. We understood why the normal distribution is so powerful. We also understood, what is a normal distribution. We understood why is it so powerful. We looked at ways to generate normal distribution, some online tools. We understood the rules of normal distribution, or the way a normal distribution is distributed. I can call it as rules of normal distribution. We understood what is a Z-score. We understood the skewness. And we also looked at how to convert a non-normal distribution into a normal distribution. So does all the natural phenomena follow a normal distribution? Yes, most of them. But is it the only distribution in statistics? No, there are a lot of distributions. A data can follow a lot of distributions. But most of the natural phenomena, we have seen that it follows normal distribution. If you think IQs, age, weight, height, any natural phenomena, most of them will see that this is close to a certain value of mean and standard deviation, and then there are some deviations, some exceptions here and there. So having said that, today we tried to cover a lot of ground on normal distribution, and these information will come in very handy when we study subsequent topics. I have tried to simplify the concepts of normal distribution as much as possible, and in this video series, as I have said, that we are committed to bring statistics to all of you in a way which is easy to understand and digest. I hope all of you have liked this video. If you like the content, then do share, subscribe to this channel. Let us know your feedback, your comments, and we deeply appreciate all your feedback and comments. If you want to enroll in the course, then do click on the link below. Till then, happy learning. So today we are going to expand the concepts which we have learned from the first two sessions, and we'll deep into the world of central limit theorem. We'll go much deeper into the world of central limit theorem, which I believe is one of the most powerful inventions in the world of statistics, because a lot of problem can be solved using central limit theorem. Apart from that, we'll also understand how we can use actually Z-score and p-value. So in the previous video, we have seen how to calculate Z-score. And here we'll see how to use Z-score and p-value. And in the process, we'll also understand the difference between population and sample. So population and sample. And this will pave the way for us to dig deeper into hypothesis testing. So let's get started with understanding the use of Z-score and how is it related to p-value, and what is p-value and how is it so important. So let's get started. So in statistics, we do two major varieties. One is descriptive statistics and one is predictive statistics. That means we want to predict something, right? Suppose if I give you a problem, right? Or I give you a scenario and I ask you what will happen next, which means essentially means that you have to predict something. Like for example, if I tell you, say, who will be the next president of, say, USA. As you know, the presidential elections are coming. So if I ask you who will be the next president of USA, and I hire you as a statistician and I ask you to make some predictions. Suppose we have candidate A, suppose the two main candidates are candidate A and candidate B. Now, if I ask you, tell me what are the chances of candidate B being the next president of USA. Now, what you can do is you can collect a lot of data. So you will collect a lot of data in the form of maybe opinions from different people, different agencies. You will collect all the data, do some analysis, and if you have to find out who will be the president of USA and what are the chances of candidate B being the president of USA, you will analyze this data, for example, and then you will come up with something called a p-value. So So if I ask you, tell me what are the chances of candidate B being the president of USA. So you collect a lot of data, then you calculate something called p-value, and this p-value, in this case, if we just want to find out the chances of candidate B being the president of US, so we basically say, we ask different people and say, will you vote for candidate B? Will you vote for candidate B, right? And you get yes, no's and everything. Now, after doing all calculations, how to do all the calculations and everything, that let's just park it. We'll look at it. Suppose after doing all the calculations, we find something called a p-value. Okay. Now, this p-value basically denotes the chances of candidate B being the president of US, because the entire analysis I am running on this particular hypothesis, that what are the chances of candidate B being the president. So we analyze the data, we calculate something called a p-value, and suppose if we get a say a p-value of 0.8, for example. Now that means that the chances of candidate B being the president of USA is 80%. So we take the data, we take a hypothesis to start with, we collect the data, we do the analysis, we calculate the p-value for a particular incident or a particular question. So first is we build some kind of question or hypothesis. We'll look at in a bit more detail with hypothesis testing. So if you are already aware about hypothesis testing, some of these things may look as if a bit disjointed from that hypothesis testing. These hypotheses right now, don't worry about hypothesis testing. Just think of it like a belief at this point. So you should think like this, that we have a hypothesis, we collect data, we do some analysis, and then we get p-value. Now after doing all these things, so this is my hypothesis, right? This is my hypothesis with which I am working, and after doing all this, I get a p-value of 0.8, which means that the chances of candidate B being the next president of USA is 0.8. However, having said that, when we talk about null hypothesis and alternate hypothesis, we'll see a slight difference from what we had just said. I mean, we do it a bit differently, but the basic principle is this. I have hypothesis, I take the data, I do some analysis, I calculate the p-value. And here the hypothesis, as I said, is candidate B being the president of USA. Okay, so I am asked these questions: what are the chances of candidate B being the next president of USA? And my answer is, going by all the statistical analysis, the chances looks like 80%. Okay, so p-value gives me the chances of a particular incident being true. Here the incident is that candidate B will become the next president of USA. I guess it's clear so far. Now what we'll look at is how p-value is related to the Z-score. Z-score is something which we have seen in the last lecture. If you have not watched the last lecture, please go and look at the last lecture, and then come back to this lecture. So now let's look at how Z-score and p-value are connected. So let's take a normal distribution. So this is a normal distribution, not a very well drawn normal distribution, but I think to some extent at least we are able to understand it's a normal distribution. Fair enough. So suppose this is my mean. And say my mean is 50 and my standard deviation is say 5. So simple one only. This one is 55. This is 60. This is 65. This is 45. This is 40. This is 35. So as you can see, I since the standard deviation is 5, I have gone up to 3 standard deviation to the right and 3 standard deviation to the left. Now, suppose I ask you a question that what are the chances? Suppose this is a distribution, right? So behind the distribution, what is there? How do we get this distribution? So we have data. From this data, we can draw this distribution, and this side maybe this side is my actual data elements, and this side is my frequency. So from the actual data, which has got rows and columns, and the actual data can probably range from say 0 to 70, 20 to 70, for example. Suppose this is my data. From these data, I have drawn this graph, which looks like a normal distribution. Now I ask you that suppose from these data, I pick up a random data point. Okay, these data, suppose here I have data, which is nothing but rows and columns, right? Any data is nothing but rows and columns. In this case, this is only one. It is only one column which we are looking at. Actually, I should not call it as a rows and columns. In this case, this is just one column. Multiple rows, right? So now, if I ask you that what are the chances if I randomly pick up one row from this particular data, which looks like this, what are the chances that will be less than 65? Will it be very high? Will it be low, or what? So if I ask you that, hey, you know what? I have this data and I know that this follows a normal distribution. What are my chances that I will pick up a data point which is less than 65? When I say I pick up a data point, I can randomly choose a data point. I do not know what the data point is. I just want to understand what are the chances of it being less than 65. Similarly, say what are the chances of a random data point being say greater than 45. what are the chances of a data point being less than 30, say 32, for example. So let's look at these examples. Okay. So in this case, what are the chances of me picking up a random point which falls anywhere in this distribution? Think intuitively. Right now, nothing. Don't worry about anything. Intuitively, do you think the chances should be more or less? On a count of 3, 2, 1. The answer is the chances should be very high because the entire distribution is on this side, right? So if the chances are high, it is very good. How high? How much? Just quantify. Let's quantify with a number. So what we'll do is we'll calculate first the Z-score of 65. What is the Z-score of 65? That is x minus mu by sigma. So in this case, x is 65 minus mu, that is 50, divided by 5, which is 15 by 5 is 3. And we also know that it's 3. So this is 3. The Z-score is 3, which is okay. But how do I convert that into a probability, into a p-value? So for that, we use something called a Z-table. This Z-table you can just Google and you will find, you can download this Z-table. It's not something which I have built. It's already there in the internet. You can download it and you can use it. So if I come to Z-table, the way to read Z-table is, so here we got a Z-score of 3. So from Z-table, what we get is p-value. So in Z-table, what we can do is, we can pass the Z-score and get the p-value. So let's look at the Z-table. So here the Z-score is 3. So 3.0 and here is 0, 0. So that is fine. So 3.00 will be this point. That is 99.87, which is okay, 0.9987 or 99.87%, whatever. So let's come here. So what it is saying is, if this point is my point in question, which means if this point is 3, which in this case it's 3, here this is like 50 and this one is 65, the Z-score is 3, which means the chances of anything picking up randomly from the left hand side of this point in question is 99.87. or a p-value of 0.9987. Now if I ask you what are the chances of picking a random data point from this distribution which is greater than 65, that will be 1 minus, which is this side. If the total is 1, then this will be 1 minus 0.9987, which is 0.0013. Not 13%, 13, and then you can multiply it with 100 and you will get 0.13%, right? So let's drop this off. So let's look at few more examples. So the first answer what we got is now less than greater than 45. Greater than 45 means I want this side, right? The right hand side. And intuitively we can see that right hand side should be more. Greater than 45, the chances of you picking a random sample which is greater than 45 is actually more. Now how much more? That's the question. So 45 we can clearly see that z-score of 45 will be -1. How? Because here it will be this will be, if this is 45, if this is 45, then this will be -1. So here the z-score is -1. Now what that means? Now let's go to the same z table. When the z-score is negative value, then we come here. So here we got a z-score of -1, which is this point. However, here, which means the shaded region percentage is what I have got. So the number which I have got is 0.1587, right? How did I get there? Again, let's come back. A z-score of 1, and here this is 0, 0, which means the value which you are getting is actually this side of the curve, and I want this side, which means if this side is 0.1587, then this side should be 1384, which means 84.13%. So the chances of we picking up a random point is greater than this point in question is 84.13. So for a negative z-score, we get this side, which is this value, but we want this side greater than 1, greater than 45, z-score greater than 1, this region. In this case, this z-score, this is 45, so I want this region, and the chances is 84.13%. So let's come back. This is next one, less than 32. Less than 32 should be this side and should be very, very low. Just intuitively, if this is 32, for me picking a random point here should be very low. Intuitively, we know that. So just let's look at 32. So if we pick up put 32 here, we get -18 by 5, which should be minus 3.6, I guess. Minus 3.6. So let's see if you can find minus 3. Oh, minus 3.6 is not even here. So let's pick up, say, 34. Say let's do 34. So this 34 should be minus 3.2, which means the Z-score is minus 3.2. So less than 34 means this region is what I'm looking at. And intuitively, we can see that it should be very low. Let's see how much. So 3.2 is this much, is this value. So 3.200. Had it been like say 3.21, then we would have picked up this value. Say, let's say, can we pick up minus 2.77? So minus 2.7 is here, and 77 should be this point. 2.7 and 77, and that should be this point. 2.7 minus and 7. Similarly, say minus 2.14, minus 2.14. That's how you should read the Z table. Okay. So now minus 3.4, 3.2 is what we have got, which is 0.007, which means this side is 0.007, which means the chances is 0.07%, very low. So 0.007 is the p-value which we have got. Now we have to multiply it by 100 and we get this. So greater than 70, let's do the last one. Or maybe say, yeah, let's do greater than 70 is actually a high number is what I feel. So let's do say greater than say 57. Greater than 57 means this point. This should be 57. And greater than 57 should be this region, which technically through naked eyes looks very small. But how much small? Let's figure out. So this is now 57. So this is like 7 by 5. 7 by 5 is 1.4. So now let's come to the Z table. Let's take 1.4. So 1.4 is this much, which means region to the left is, so what I want is this point, right? This is my Z-score of 1.4. I want this region. However, the value which we'll get here is actually this region. So this is this region. Right? So this one is 1 minus 9192, which ideally should be 0.08, which means if I just multiply it, it should be around 8%, a bit more than 8%. Okay, I hope this part is clear now, because this is the foundation, this is the base, which will help us to solve a lot of problems. So we have completed now understanding Z-score and p-value. Now we'll understand what is a population and what is a sample before we go to central limit theorem. So population and sample. So in very simple terms, population is my superset and the sample is my subset. So population is a superset and sample is a subset. Now let's get some examples. Suppose I ask you what is the population of India, which means it like contains the entire population of the country, which should be around approximate, say 130 billion, 130 crores, right? 130 crores population of India. Now suppose if you have to do an exit poll, right? If you want to do an exit poll, do you think it's feasible that we go and ask all these 130 crore people that whom did you vote for? It's impossible, right? So what we do is we create subsets. We create subsets where we divide people by age, gender, occupation, mother tongue, and so on. Lot of criteria, not only these four. And then we pick up few people from here. We pick up few people from here, we pick up few people from here, we pick up few people from here and ask them. So suppose here we have got say multiple age groups. So suppose for age group 60 and 70, we have say 5 crore people. So we'll not ask all those 5 crore people. We'll go and ask say 2000 people who will represent this 5 crore people. That's something which we assume. Now, while sampling, a lot of errors can come if the sampling is not done correctly, right? So by age, gender, occupation, mother tongue, and so many other criteria, that's the statisticians uses and then chooses a subset from the superset and does the statistical analysis on the subset, because it's impossible to go and ask 130 crore people whom did they vote for, right? So maybe out of these 130 crore people, they will ask say 1 lakh people, and with good statistical agencies they can if they do the sampling correctly, if they choose the right set of subsets, then 1 lakh, 1,50,000 or even less. I mean, the more expertise you have, the less subset is what you require. And then based on that, based on these 1 lakh, we make decision for these 130 crores. That's the power of good statisticians. In some agencies, it's even less. I have seen agencies who have done exit polls for just by selecting 50,000 people out of a population of 130 crore people, and their prediction was like very, very close, right? So it's not possible that we go and talk to everyone. So we choose a sample, we choose a subset from the entire data set, and then we do the analysis on that, and we assume that this subset represents the superset. Like, for example, suppose all these are my data points. All of them are like one individual. And dot dot dot. Now we can choose subsets like this, and it's important that the same subset can be repeated, which means the person who represents a certain age can also represent a certain gender. There is no hard and fast rule that for each experiments or while choosing each subsets we only choose the unique set of people. Not necessary, right? So we can choose like this. Here we are just choosing 4, one set with 4 people. So for each sampling criteria, we are saying say pick 4 people. Though in exit polls they do not pick 4 people, so don't mix it up with that. This is just for representation and for this purpose, just for understanding purpose. Suppose, for example, we pick up 4 people each, and we choose from here. Say here also I say choose 4 people, and then we do the analysis independently on these guys. We do some calculations, and then whatever result we find, there is something which we can tie back to the main population, and we can say that the results which we have got from these samples or this subset is a representation of the entire population. So now I think we have got a fair idea on population and sample. Now, keeping this in mind, we are going to understand central limit theorem. So let's look at central limit theorem through an example. Say I have a data set where I have around 20 records. So here, as you can see, I have got 20 records. Around 20 records. Now what I'm going to do is, I'm going to randomly choose, by the way, here the word which is very important is random. I cannot pick and choose at my wish. I cannot say, okay, I want this, I want this, I want this, I want this. No, that will not work. I have to randomly just close my eyes and pick up 4 people. Similarly, in the previous example, when I was showing is when they sample, when they create subsets. Suppose they have created a subset where all the occupation is, say, IT professional, right? Now they know that these say 20 crore people are IT professionals, and I know that, okay, I want to choose, say, 50 people from there. I cannot make bias in my mind, say, okay, I want these people, this. I'll suppose think like this, as if I'm closing my eyes and I say, okay, number 21,000, okay, number 15, okay, number 30. So it's like randomly I'm choosing. Because if I do not choose with random or randomness, then the entire purpose gets defeated. The tests cannot be done on bias. It has to be random. So suppose I have randomly picked up, this is something which I have already done before, so that I don't lose time in doing that. So just assume that, okay, I have not done any cheating and I have randomly picked up. So suppose I have picked up these four numbers randomly from here, 5, 7, say 32, and say 11. Last one. And once I have picked up these four people, what I have done is I have calculated the mean and the standard deviation. So this is like a mini distribution. This is the main distribution. Main distribution, I call it as a population. And say this is a mini distribution. So I pick up these four numbers. After picking up these four numbers, I take the mean and I take the standard deviation of just these four numbers. Again, I pick up again four numbers from here, which are these ones. Again, four number picked up from here. I calculate the mean. I calculate the standard deviation of these four numbers. Again, four numbers here, the mean and the standard deviation. Four numbers, the mean and the standard deviation. Okay. Now, what we shall do is, let's come here. Standard deviation is something which we do not need. We'll work with the means. So for all these subsets which we have taken, for all these four number subsets, we have got the means for all of them. We have also calculated the standard deviation, but we do not need it. So we have taken all these means. So as you can see, these means. So we have formed another data distribution where we have taken all the means. So these ones and these ones, all these means. And we have formed another data distribution because the collection of data is a distribution. So here we have created a distribution of means. So we have taken all the means and created another separate distribution. Now, what central limit theorem says is that when we have formed this distribution of means, if I plot them, then if I plot them of plot of frequency, what I get is a normal distribution. Of course, I have to do some some amount of sampling, which means if I just take two samples, if I just take this one and this one, I'll of course not get a normal distribution. So we have to do substantial amount of sampling, and it depends on how much data you have. The more data you have, the more number of sampling you need to do. So central limit theorem has got three distinct and very important formulas. First formula is when you form a distribution of means, if you plot them, if you plot their frequency, you will find that they are following a normal distribution, which is That means this particular distribution, if you plot, we find that it follows a normal distribution. That's the first hypothesis. Second hypothesis is, since this is also a distribution, I can take its mean also. I can take the mean of all these numbers, and suppose I have done that, and I can see that this is 44. So this mean is 44 is what we have found. Ignore all this right now. I'll talk about it in a moment. So all these numbers, all these particular numbers, like for the distribution of means, if I calculate the mean, which means mean of the distribution of means, if I calculate, I get it as 4.86. Now if I call this as a mu bar, this mu bar is 4.86. Central limit theorem says that these mu bar and the mu, which is the mean of the population, mean of population, right? After some time, these two will come very close and can be equal also, or even if it does not come, even if it does not equate, it will like come very close. So these mu bar will come very close to mu. So here this is 4.86. Let's look at what is the original mean. It's 45, and we can see that after 20 iterations of randomly picking up numbers, what we find is that the mean of this distribution of means, they have come very close to the original population. That's the second hypothesis. So we have learned two things from central limit theorem. One is distribution of means when plotted will form a normal distribution. Will form a normal distribution. This mu bar is mean of distribution of means. And this is population mean. Point number 3, third hypothesis is sigma x bar is equal to sigma by square root of n. Sigma x bar is standard deviation of distribution of means. This is standard deviation of the population. and this n is number of samples. So in this case, if I have to run the central limit theorem, I have to ensure that this n is constant, which means every time I have to pick only 4 or only 5. For one iteration, if I just pick 4, second one I pick 5, then I will not be able to apply central limit theorem. So here also, if we see, if we calculate the standard deviation, this is 14.34. What is the standard deviation of the population? 25.5. If I divide it by square root of 4, which is 2, it should come to 12.77. And we can see that here we are 14.34, and it's coming very, very close. So you must be wondering what is these numbers. So when I had taken the first two data point, first two means, this was my mean of the distribution of means. Then first 3, this, then first 4, this. And as you can see, with time and time, the more iterations we do, this is coming closer to the original distribution. Here also we can see that this is decreasing and coming close towards this 12.77. Ideally this should be 12.77, right? Because if you look at the formula, sigma is 25 and we have taken 4 samples, so 25 by square root of 4 is 2. That comes to 12.77. So this side is 12.77, and after a few iterations, this is like 14.3, and it's coming closer. If we take few more iterations, it will eventually go and come very close to 12.77. So in essence, these are the 3 formulas of central limit theorem. Now, couple of things which we have to understand, which are the assumptions. So number 1, the population can be of any sample, or sorry, the population can be of any kind of distribution. Does not mean that the population has to also be a normal distribution, not necessary. So the first assumption is population can be any distribution, can be skewed, can be normal, can be anything. Can be any kind of distribution. Number 2, when we choose the sample, we have to choose them randomly. So random selection. That's important. Number 3, samples should be independent, which means if I pick one sample, the selection of other samples should not have any impact. So let me independent, which means, for example, if I choose 5, this 15 has no impact. So I have chosen 5, then I've chosen 15. So 15 has no impact whether the previous number we chose was 5 or not. It's independent. It got independently chosen. So we have closed our eyes and said, okay, 5, 15, 12, 14. So 15 has no relationship whether we chose 5 before it or 32 after it. So that's another assumption. So the next assumption is the sample size which we should choose, that should not be more than 10% of the population. Should not be greater than 10% of the population. And number 5, if the population is like asymmetric in nature, like right skewed or left skewed, this is not left skewed by the way, if they are asymmetric, which means say this one or this one, then we need to choose more samples. And if they are symmetric, then we need to choose less samples. So for symmetric population, or in simple terms, things, if the distribution is like more or less normal, then we can choose, we can limit the sample size to less than 30. We should choose sample size which is less than 30. For asymmetric population, we should choose more samples. Okay, I hope these assumptions are clear. Now what we'll do is we'll run through a quick simulator where this concept will be even more clear. So this is the link of the simulator. You can also go and practice yourself. And when I learned central limit theorem for the first time, I got very confused initially. And then I used this simulator and everything started to make sense very quickly. So let's look at the parent population. Say parent population. We say that it doesn't matter what is the parent population. It can be normally distributed, non-normally distributed, can be anything. Now what I'm going to do is, so I just distorted the population as much as possible. So for this population, I know the mean and I know the standard deviation. Now what I'm going to do is, I'm going to pick 5 samples here randomly. So these here, as you can see, 5 samples I am picking randomly. This n is equal to 5. And then once I have picked up these 5 samples, I calculated their mean, and that is my distribution of means. And as you can see here, since the points are more or less here, the mean has to be here, right? This is only one point here, so this mean is like very close to these data points. So again, I choose randomly 5 points. I get a mean, which means like I'm here. I've got these 2 points, and I have started forming my distribution of means. I've got 2 points. Here I've got 2 points. Again, one more. I've got 3 points now for my distribution of means. And as you can see, I've done like 3 repetitions. Now what I'll do is I'll like fast forward. I'll do it 10,000 times. Now it's like 10,003 times because I did 3 times before, and now it's 10,000 times. Now for this distribution of means, if I want to feed it to a normal distribution, I can see that it's more or less fitting like a normal distribution. So my hypothesis 1 is proved, and we can see that it works here. What was the second hypothesis? That these mean this distribution of mean, and this mean will be coming very close to each other. And if I look at it, it's like 15.47 here, and here it's 15.5, very, very close. If I do it, say 10,000 more times, now I have done 50,000 times, and as you can see, this mean is like 15.49, and this mean is like 15.47, very, very close. If I take one place of decimal, then it has already merged. My third point was standard deviation. So standard deviation for the formula was sigma x bar is equal to sigma by square root of n. So in this case, sigma is my 9.96, which is this, divided by square root of n. N is, I'm taking 5 samples, so square root of 5. So now let's just calculate and see how much it should come and how much it has come. So square root of 5, I guess, should be 2.23. 9.96 divided by 2.23. That is 4.46. And you can see here it's 4.45. Very, very close. So let's do one more. And it doesn't matter how many number you choose. It will still stay the same. Another distribution. Animated. I'm now taking 10 samples, and then I get my distribution of means. So here my standard deviation is 9.14. So first let's do 10 square root. 10 square root is 3.16. So 9.14 divided by 3.16 is 2.89. So here my sigma x bar should be 2.89 after few iterations. We'll see. So animated, again 10 samples, and I get their mean. Now fast forward 10,000. I have tried to fit the normal distribution, and I can see it's almost fitted, or it's fitted quite well actually. Here the mean is 14.38, the mean is 14.41, almost merged. The standard deviation is 2.93, and we should have got 2.89, again very close. Let's do few more rounds and see. Now after 60,002 rounds, we can see now the standard deviation is 2.9. Here this is 2.89. Here we see that the mean is 14.39. Here you can see the mean is 14.38. And now it fits the normal distribution even better. So you can play around this tool and get a very good idea about central limit theorem. And in the next lecture, what we'll do is we'll look at hypothesis testing. We'll understand what is a null hypothesis, what is an alternate hypothesis. Then we'll look at false positive, false negative, type 1 error, type 2 error. And then we'll look at some problems. So in order to do hypothesis testing, which we will learn later in the next series, the basic building block is central limit theorem. So we apply central limit theorem and get answers of hypothesis testing. So here, this part, this analysis, under a lot of scenarios, we use central limit theorem. Not that for this case we will use central limit theorem, but just assume that if we go this path, central limit theorem, and there are other techniques as well, not only central limit theorem, but in this context, so we establish a hypothesis, we collect the data, We do some analysis by using central limit theorem and or some other techniques, and then we calculate the p-value, and then we make some inferences. And central limit theorem, as I said, is one of the most powerful techniques in statistics. So I hope all of you liked this session. If you want to subscribe for the course, you can click on the below link. And if you have liked this session, I request all of you to share, click the bell icon, subscribe to this channel, so that we can make more content and we can try to make statistics much easier to understand for all of you. Having said that, I thank all of you for watching this video and happy learning. Hello everyone, welcome to another session on statistics. So today we are going to cover a very interesting area of statistics. And from my experience, I have seen a lot of people struggling with this particular concept. So today we are going to cover hypothesis testing, and we will look at what a null hypothesis, what an alternate hypothesis, under which scenario do we do hypothesis testing, and how do we use null hypothesis and alternate hypothesis in making a statistical assumption or hypothesis being declared as true or not true. So let's get started. So let's look at hypothesis testing. So as I have said in my previous lectures, that whenever you're trying to learn a particular topic, try to understand the meaning of each word. So here we have two words, hypothesis and testing. So if we try to dig deeper, hypothesis means what? Some kind of belief, some kind of assumption, some kind of intuition. Now this belief, assumption, intuition, whatever we have, we need to do some testing and see whether these belief, assumption, intuition are, whether they are valid or not, whether they have got some base or not. I can never say whether it's true or not, but we can see what's the probability of this belief, assumption, intuition being true. How likely are these to be true? Fine. Now what we will do is we'll try to do some testing. So the answer to this question can only be done through some testing, right? So we have some belief or assumption or intuition, and we want to understand how likely are these belief, assumption, intuition to be true, right? Through some kind of testing. What kind of testing? Some kind of statistical testing. Let's go step by step. some kind of statistical testing we are going to perform. So now let's understand what are the two main pillars of hypothesis testing. And even before that, let's go through a scenario and let's try to understand how a belief or an assumption or an intuition gets formed. So suppose you go back to the time machine in 2019. Actually, we want to go to 2019 looking at the current scenario. Jokes apart, so suppose you are in 2019 and you have an hobby of visiting your friend's place over the weekend. So every weekend you go to a friend's place to chill out, to have some nice time during the weekend. But the statistician within you, it refuses to give up. It always tries to find something. So what do you end up finding? So you go to your friend's place and start observing how the kids are leveraging their weekends. So suppose in 2019, you went to 50 friends' place over the weekend. Maybe 2 weekends you kept for yourself, which is fine. So you visited 50 friends, and what you observed is that out of these 50 friends whom have got kids, 40 kids are watching TVs. Okay. So suppose this is your universe, this is your friend's universe, right? These are the 50 friends you have got. So you start making an assumption based on these 50 friends, which in your case you can think of being population. In your case, by the way, so you can think, okay, around 80% kids are watching TVs, right? So 40 by 50 is 80%. So you make an inference that around 80% kids are watching TV based on what you have seen. Fine, no problem. This is okay. Now you are in 2020. And after all lockdowns and social distancing will still stay. After all lockdown got relaxed, you started visiting your friend's place again, of course maintaining social distancing, and you again visited. You have made more friends this year, so you have few more friends, and this year you went to around say 30 friends place. Now this time here you had 70, you have 50 friends. So in this case, in 2019 your number of friends was also 50. So in this case, consider this as a population of friends with your context. In 2020, suppose you have got say 70 friends, you have made 20 more friends. and you have gone to 30 of your friends' place over the weekend, right? So total number of friends is 70. That's total number of friends, total friends, right? So you have visited 30 friends and you found that 18 kids are watching TV. So now the statistician in you has become very inquisitive. So you started analyzing these two incidents. And this time you have seen that around 60% kids are watching TV. So I can say here around 60% kids are watching TV. Okay, fine. So now let's look at these two incidents. So now let's understand these two incidents. If we look at and compare these two incidents, what is the first thing which strikes us? That probably kids are watching less TV, right? But watching less based on what context? What is my base assumption? What is my base, not assumption, what is my base data? My base data is this. So whenever I am seeing less TV, it's always compared to your base data, or you can also say population, right? So from your base data and the current data, so your baseline data and the current data, when you analyzed, your analysis says that probably kids are watching less TV, which you have seen from here, but you are not sure. Why? Because you have not visited everyone. You have only visited 30 friends out of your 70 friends. So now the question which comes in your mind is, okay, I have visited 30 friends and I have seen around 60% kids are watching TV. So let me make an intuition that kids are watching less TV. Now if we have to represent this intuition mathematically, in mathematically there is nothing like less and more. Everything has to be represented through a number. So let's try to represent this mathematically, and the mathematical representation is so the mathematical representation is mu1 greater than 80%. Mu1, just consider any other variable. Okay, so that is what my hypothesis is looking at these two data, right? So now my intuition is that people are watching less TV from where? From 80%. So if I have to represent it mathematically, my mathematical representation is H1 is equal to mu1 less than 80%. Fair enough. So what is the alternate, or what is the reverse of H1? If I have to make a reverse logical statement and a mathematical statement. So the reverse logical statement of what we have seen is that kids are watching more TV. My belief is kids are watching less TV, but the reverse of it is kids are watching more TV. Right? So from here, we can now understand null and alternate hypothesis. So let's keep this example in mind. So what is alternate hypothesis? So it's generally what we believe and something which represents a change. So what we believe okay, so alternate hypothesis is what we believe and it also represents some kind of change. Actually, this is not a question mark. So if you look at this example, what we believe that kids are watching less TV, and the moment we are saying less, that's a change from my baseline data, right? Had we observed 24 people here, 24 kids watching TV, then I would have said 80% kids are watching TV and there is nothing interesting happening here. So I really don't need to bother. Nothing has changed. So here what we see is a change. Here it's 80, here it's 60. So there is a change. And that change is driving a belief. Right? So that change is driving a belief. What is my belief? This is my belief. So alternate hypothesis is something what we believe, and when we are really bothered about this belief, when there is something interesting, when there is something interesting happening, there is some change in the system which makes us believe something, right? So that is called alternate hypothesis. Now what is null hypothesis? So null hypothesis is just the reverse of alternate hypothesis. So for example, we had said that mu1 less than 80%, right? So the null hypothesis in this case will be mu1 greater or equal to 80%. Just the reverse of alternate hypothesis, something which we do not believe, right? Which we do not believe. Okay, now how to remember it easily? Look at the word null. Null means nothing, not my hypothesis, right? This cannot be my hypothesis. So not my hypothesis, null hypothesis, right? So we have two statements now. One is what we believe and one is what we do not believe. So alternate hypothesis is what we believe, null hypothesis is what we do not believe. Also remember, the entire hypothesis testing comes into picture and we start building hypothesis when we see some change in the system. If there is no change, I really don't need to bother. So we have got a null hypothesis and an alternate hypothesis. So we have a null hypothesis and an alternate hypothesis. So from this alternate hypothesis, I have formed a statement and somehow my intuition, my assumption, my gut feeling, which is my alternate hypothesis, I want that to be true. I want to prove that true. Right? Here, I want to prove that kids are watching less TV. Here, less is from the baseline data, as I said, which is 80%. So I want to prove this true. How can I prove it true? Through my hypothesis testing. So in hypothesis testing, what we do is we try to test the alternate hypothesis. Which in this case is mu1 less than or equal to 80. Sorry, my bad. Not, there's no equal to here. So we want to test this to alternate hypothesis. Rather, we want to test this alternate hypothesis through hypothesis testing. Now I have a problem. The problem is, in statistics, there is no such test through which you can test an alternate hypothesis. Problem. So, at least till now, we cannot test this. There is no such tests available through which I can test my alternate hypothesis. So this does not work. Okay, then how do I prove it? I have something called null hypothesis. So here I have a null hypothesis. So note that I have made a notation of H0 and H1. H0 here, this signifies null. Right? This is not a 0, this looks like a sigma. So I have a null hypothesis here, which is signified by H0. And my null hypothesis is mu1 greater or equal to 80%. Now in this case, it's, if you look at these two, it's not possible that it will be greater than 80. So worst case scenario, it can be equal to 80, but cannot be greater. So let's make it equal. So see, we have null hypothesis, which is another weapon. So what we can do is, there are some tests available through which you can do hypothesis testing using null hypothesis. Fine. So I cannot use alternate hypothesis to do hypothesis testing. I can use null hypothesis to do hypothesis testing. And here starts the fun. I want the outcome of this null hypothesis not to be true. Now in statistics, and especially in the world of probability, we cannot really say true or false. We can at least say that it has a high chances or it has low chances, or the probability is high or the probability is low. So in this case, what is my aim? What is my objective? My objective is that when I do the statistical tests, I want the probability of this particular statement to be very, very low. I repeat, when I do hypothesis testing, I use null hypothesis, and I want the outcome of this statement, which is the null hypothesis. This statement should have very low probability. This statement should have very low probability. Which is strange, right? So now the next question comes is, fine, high, low, I understand, but if it comes low, then what happens? If it becomes high, then what happens? If null hypothesis becomes high, then what happens? Right? So you have a lot of question in mind. But before that, let's understand something, that in the world of data, there is nothing called high or low. Everything is numbers. So when I say low probability, what does a low probability means? In this case, generally, with hypothesis testing, we say that the low probability can be said about an event if its chances of occurrence in reality is less than 5%. Generally, there can be some exceptions. Someone can explicitly mention some percentages, but if nothing is mentioned, always assume that when we say low probability, we mean that the chances of occurrence of that particular event is less than 5%. Now, if you recollect what we had learned in our previous videos, this probability is also denoted as p-value, which means this p-value should be less than 0.05. P-value is not calculated in terms of percentage, but 5% is nothing but 0.05 only. So if you recollect our last video, we had actually showed you how to use Z-score and get a p-value. P-value is nothing but the probability of certain thing or a certain event being true. So the probability of the kids watching TV rather I would put it like this: the probability of 80% kids watching TV in reality should be less than 5% if I want to establish my belief. What is my belief? That they are watching less than 80%. So in this case, I have to, or rather I will expect, I will hope that when we run some tests, we will find that this particular statement has got very low probability or very less chances of occurrence. Now, why are we doing this test? As I have mentioned before, because I have not visited everyone, else so I could have passed a judgment. Here I am not able to pass a judgment because I have not visited everyone. I have only visited 30 people. Now the question which comes is, the way you have to think about this is, that is this number 30 and this 18, right? 18 out of 30 kids watching, is it enough to make an inference, right? Is it enough to make an inference? So when I'm interested in this kind of inferences, when there is some kind of change, here we have seen some changes, but is the change enough? Because I'm only talking to 30 people, I'm not talking to the entire population, right, of 70 people. So the results which we get for 30 people, is it enough to say that the same will apply for 70 people also? Okay. So now, how do I do that? Using hypothesis testing, where we have a null hypothesis, we have an alternate hypothesis. So now let's take a scenario, and that will probably make things more clear. So suppose I have I have a hypothesis to test that let's start with H1, that mu1 less than 70. Now what is this 70? 70 or 70% or whatever, right? What is this 70%? Say 70% people ordering pizza over a weekend, right? So we analyzed again data of two distinct time frames or two different observations or set of observations. So in 2019 or in 2020 Q1, you again spoke to few of your friends and just asked them casually, do you order pizza during the weekend? So you have 50 friends and you asked all of them, and 70% people said yes, we do order. In Q2 2020, you were not able to connect to everyone, so you asked 20 people, 20 friends, and they said so 50% of them said that yes, they order, which means 50% say that they didn't order during this frame. So my baseline data is this, right? And I want, or rather I can see that there is a trend. I build a hypothesis that probably people are ordering less pizza. What is less? From where? From this 70%. So mathematically representing mu1 is less than 70%, and that is my alternate hypothesis. Here I have observed a change, a strong change rather, to make some kind of assumption, right? And in this case, my null hypothesis is that my mu0 is ideally it should be greater or equal to, but in this case it cannot be greater in any case. So let's be lenient and let's put equal to. So now, as I said, I cannot test H1, so I can only test H0. So now I will suppose do some tests. What tests? Don't worry about it right now. We'll look into it detail. So suppose we have done some statistical tests, and the outcome of these tests are nothing but p-values. Right? P-value means the probability of something being true. So here, for this scenario, suppose we got a p-value, and here also we got a p-value. Suppose this p-value is 0.04. So ideally, this p-value should be 0.96. If this is 0.04, of course, this will be 0.96. And just to make things logically good, so now it should be like it has to be a binary condition. Either it's less than 70 or greater or equal to 70. Right? Though technically we can see that here the greater part doesn't really matter. So if I have got a p-value of 0.04 for my null hypothesis, then my p-value for alternate hypothesis will be 0.96. Now what does this signify? So ideally, if the p-value of your null hypothesis, which we can test, this we cannot test, by the way, this we cannot test, but this we can test. So if we can get the p-value of H0, we can also derive the p-value of H1. So this cannot be directly achievable through statistical tests. We achieve the p-value of H0 or the null hypothesis, and from there we can extrapolate alternate hypothesis if the conditions are made binary. That's the reason why, just for your understanding's sake, I made it greater than equal to and less than 70. So now I have a p-value for null hypothesis. I have a p-value for alternate hypothesis. If this p-value, as I said, goes below 0.05, then I said, hooray, I have made a failed experiment. So here my experiment can only be done with H0, not H1. And I want this experiment to fail. I want H0 to fail and give me a very low probability. Right? How did you calculate? If you think, okay, chalo, how did you find this 0.04, 0.96, 0.55? Right now, I've just cooked it up. How do we actually do this test? Let's not worry right now. But let me just give you a spoiler alert. It's not very difficult because by this time you already know central limit theorem. So now we have got a p-value of 0.96 and 0.04. Now this 0.04 is less than my threshold, which is 0.05, until specified, as I said, in statistics. It's 0. This number, this threshold, we always consider as 0.05 until and unless specified. Where do we specify? Say, for example, in healthcare, for very sensitive tests, probably they want this 0.04 to be, say, 0.001 because there's high chances, right? So the p-value of 0.04 means that there is only 4% chance that this particular statement is true. If that is the case, then the chances of this person or this statement being true has to be 96%. So my objective was to test the alternate hypothesis, which I cannot do directly. So I will test through null hypothesis, do some calculation, get a p-value, and then look at whether the value of this p-value is less than 0.05 or not. So in this case, we see it's 0.04, which is less than 0.05. So in that case, what we can do is, we can say that, sorry, Mr. Null Hypothesis, we have to reject you. And if that happens, so I have to accept the alternate hypothesis, which I always wanted. So I wanted to accept the alternate hypothesis, but that was not possible directly. So I want that the probability or the p-value of the null hypothesis becomes as low as possible. And that's my best chance that my case will get pushed. What is my case? Alternate hypothesis. So now let's look at some of the outcomes of null hypothesis and alternate hypothesis. So let's open Excel. So we'll say null hypothesis p-value, alternate hypothesis p-value. And here outcome of null hypothesis and the outcome of alternate hypothesis. Which is not required to save this. So now say my null hypothesis is 0.04, which means my alternate hypothesis is 0.96. So outcome of null hypothesis is reject null hypothesis. And this is rejected. We can say that we can accept alternate hypothesis. So now let's take another scenario, say 0.58, right? So, or rather let me put it, say 0.07. So this becomes 0.93, right? So in scenario 1 or in row number 2, the null hypothesis, the p-value of null hypothesis is 0.04, which automatically means that the p-value of alternate hypothesis will be 0.96. So in null hypothesis, suppose it is now 0.07, which means alternate hypothesis 0.93. Now what do we do? Right? So in previous case, I rejected the null hypothesis since it was the p-value was very, very low, and I accepted the alternate hypothesis because the p-value is very, very high. In this case, 4% and 96%. Now for null hypothesis, if this is 0.007 and this is 0.93, then what happens? So can I reject the null hypothesis now? Unfortunately, no. Because I had said that this is the range, this is the number or the matrix which we should take as baseline. Right? For any statistical tests. So now here we can see that the p-value of the null hypothesis is quite low, or rather not quite low. It is 0.07. So in this case, what shall we do? Can we reject the null hypothesis? No, of course we cannot, because it is 0.07 greater than 0.05. So we cannot reject the null hypothesis. So then we can accept the null hypothesis, right? If we cannot reject. And in this case, we can say reject the alternate hypothesis, right? Unfortunately, not right. And this is where a lot of guys make mistakes. So pay attention here. Here, can we reject null hypothesis? No, we cannot say that. Can we accept null hypothesis? No, we cannot say that either. Why? Or rather, can we reject null hypothesis? No. Can we accept null hypothesis? No, we cannot. Why? Because if you look at it intuitively and carefully, still the chances of the null hypothesis being true is only 7%. Now, how can I accept something whose chances of occurrence in reality is only 7%? So in this case, I cannot reject null hypothesis. Neither can I accept the null hypothesis. Why? Because as I said, the chances is only 7%. So what do I do? In this sort of scenarios, we project like this: fail to reject null hypothesis due to lack of statistical relationship or whatever, right? So in this case, we cannot reject the null hypothesis, but we cannot accept it either, because its chances of occurrence in reality is very, very low. It's only 7%. So my answer is, we will say in this scenario, we'll say we fail to reject the null hypothesis, which means I do not have enough evidence against my null hypothesis, right? This 7% is not a good enough rational, right? Only 7%. So we cannot accept, rather we cannot reject null hypothesis, but not can we accept the null hypothesis either, right? So this is 7%, and we say that fail to reject null hypothesis due to lack of statistical relationship evidence, whatever. And here we can say we do not have enough evidence to prove alternate hypothesis. We can only prove alternate hypothesis if we reject the null hypothesis. In this case, I am not rejecting, right? So if I am not rejecting, I cannot make the alternate hypothesis reject as well. By the way, it's a spelling mistake, right? So in this case, we say fail to reject null hypothesis, right? Now the question is, if you ask for an example, like for example, in law, a lot of times we say that we are letting this criminal go, though we know that he is a criminal, but we are letting him go because we do not have enough proof against him. But we know that, he's a criminal. So that's the kind of scenario we have come now, right? We don't have enough evidence to prove that the alternate hypothesis is true. We don't have enough evidence to say that the null hypothesis is false, right? So in that case, can we not ever accept a null hypothesis? The answer to that is yes, you can. You can accept null hypothesis. But under what scenario? So if the p-value is of the null hypothesis is say 0.96, for example, and this is 0.04, right? So in this case, I can come and say yes, we can indeed accept the null hypothesis. Why? Because we have high p-value for null hypothesis. So in this case, null hypothesis, the p-value of null hypothesis is very high. And in this case, 96%, right? If I can reject it below 4%, I can also accept it above 95%, right? So in this case, if my p-value is greater than 0.95, then I can accept null hypothesis and I can reject alternate hypothesis, right? Now, in reality, the chances of occurrence of this particular problem is very, very less. It's very unlikely that in your test, you will find a p-value for a null hypothesis being 0.96. It will never happen, right? It's unlikely. Probable, but probably not possible, right? But still good to know. So our scenarios lie between generally these two conditions. Either we reject null hypothesis or we fail to reject null hypothesis. So later I'll also tell you that how come this is possible. I mean, under what scenario you can get a null hypothesis having a very high p-value, right? So to sum up a scenario with an use case, so here I'm not going to take a use case name or something, just think that mu1 greater than say 30 and mu0 greater or equal to 20. So mu1 is my alternate hypothesis, mu0 is my null hypothesis, okay. And I want mu0 to be having a p-value which is very, very less. Don't worry about this point, how am I getting this p-value? We'll do that in another video. Right now, let's just understand that we have some ways to do some statistical tests. We can gather something called a p-value, which is basically the probability of that particular incident happening. So here mu1 is less than 30, mu0 is greater than or equal to 20. Or rather, it should not be 20, it should be 30 only. Right? Just the opposite of this. Now, if the p-value of this particular assumption is say 0.03, right, then in that case the p-value of here will be 0.97 or 97% or 0.03 or 3%, right? If this is the scenario, then what can I do? I can reject the null hypothesis and accept the alternate hypothesis, right? And if this is the scenario, say 0.7 and 3. So if this is the scenario that the p-value is greater than 0.05 but not very high also, right? So in this case we can say that we do not have enough evidence to prove that null hypothesis is false, right? So we do not have enough evidence to prove that the null hypothesis is false, or not enough evidence to reject the null hypothesis, or not enough evidence to accept the alternate hypothesis. So now we have understood null and alternate hypothesis. So let's understand confidence interval in a bit more detail. So what is confidence interval? Now you have noticed that so far with all the tests which we were doing, I was saying that if the p-value is below 0.05, we consider the null hypothesis to be false and alternate hypothesis to be true. So let's write down p-value less than 0.05 means null hypothesis is not true. Right? Or rather, I should say the chances of null hypothesis being true is only say 2% or 1%. I said not true is may not be the right term. So here let's understand how, from where did we get this 0.05. This is, by the way, called as the confidence interval, right? But why 0.05? So let's dissect this. Suppose you are captaining a cricket team and you are playing a 7-match series. You have gone to a different country and you are playing a 7-match series. So in the first match, you did the toss. First match you did the toss, you called heads and you got tails. So you lost the toss, right? So now in this case, what is the probability that you get a tail? The probability of getting a tail is 0.5% or 0.5 or 50%, which means in reality the chances of getting tails is 50%. By the way, you have called heads, so you lost the toss, right? Second match, you again called heads and again you got tail, right? Now in reality, what are the chances that you get 2 consecutive tails? We will cover conditional probability later, but from here at least let's understand this in a slightly detail. I mean, in 2-match series, what are the different combinations which can happen? Head head, head tail, tail head, and tail tail. So the chances of getting 2 tails is 1 out of 4, which is 25%. So you lost 2 consecutive toss. So does that strike you that, hey, you know what, something is not right? Or you will feel, no, it's okay. I mean, 2 tosses, having consecutive tails, no big deal. Ideally, it's no big deal. It happens. I mean, 2 consecutive tails, what's the big deal, right? Third match, you again go. You again call tails. Sorry, you call heads, and you get tails. Now the chances of getting 3 consecutive tails is 0.125. If you just see the trend, it's just getting half every time. So the chances of getting 3 consecutive tails is 0.125, which means you have encountered an incident whose chances of occurrence in reality is 12.5% only. But do you doubt this scenario? You will say, no, I mean, it's okay. I mean, we can have. You go to the 4th match. You again call heads, and you know what? This time also you got tails. So what are the chances of getting 4 consecutive tails? It will be most probably 6.12%, 6.25, right? Let's just do the simple maths. 0.125 divided by 2, 0.625. Perfect, not 1, 2. Which is equal to 6.25%. So now you start getting a bit of doubt, because if you think logically, you have got a scenario where the chances of occurrence of something is 6.25%, and you have encountered that kind of scenario, you start getting a bit of doubt. Now in the fifth match again, you called heads and you again got tails. Oh my god. What's the chances? What's the probability? 3, it should be 3.12% around, right? Now you have encountered a scenario whose chances of occurrence in reality is 3%, 3 point something. Now you think, boss, definitely something is not right, right? So these barriers below which we generally start doubting, the barrier is kept at 5% or 0.05, whatever you want to say. And this barrier is nothing but my confidence interval. Now, is it every time that it will be 5%? Not really. I mean, in some cases, as I said before, that especially for medical cases, this confidence interval is taken to say 1%, right? 0.01, because we are dealing with someone's life and death. So we better be sure 99% about our alternate hypothesis. But this is, in general, we use this. Okay. In general. Now let's understand what are the different varieties of tests which we can do with hypothesis testing. So what are the different varieties of tests? We do Z test, we do T test, we do few other tests which I'll cover in probably a subsequent video in detail. One more area of tests which we do are called one-tailed test and two-tailed tests. So what do we do in one-tailed tests? What is the property of one-tailed tests? In case we are dealing with greater or lesser, that means I'm checking only one side, right? In two-tailed tests, we are checking equal and unequal, right? So for one-tailed test, we check if something is greater or lesser. For two-tailed tests, we check equality. So let's take some examples. Suppose I have an alternate hypothesis that the average age for doing gym is, say, less than 30, and the equivalent null hypothesis will be right. So here the alternate hypothesis is the average age is less than 30. The null hypothesis is the average age is greater than 30. So here we are checking only one side. Likewise, if you do say the average IQ of people, suppose we make an alternate hypothesis is that it's greater than 110, for example. So in this case, the null hypothesis is right. So here we are in both these scenarios, we see that we are only testing one side, and this is called a one-tailed test, when we are usually checking either the greater or lesser. Now when it comes to two-tailed tests, let's look at two-tailed tests. Suppose I say that I have made some decoration changes in my shop, and I have seen that the average footfall has changed, or the change can be increased as well as decrease, right? So that I can say that the average footfall has changed. So say in this case I say, okay, my alternate hypothesis is that the average footfall, which previously was 30 per day, is not equal to 30. And the null hypothesis is that the average footfall is equals to 30. How to do these tests we will discuss in detail, but right now let's just understand this part, that two-tailed tests denotes equality or not equality. Inequality. One-tailed tests check for greater or lesser. Okay. So now we have understood null hypothesis, we have understood alternate hypothesis, we have understood confidence interval, we have also understood one-tailed test and two-tailed tests. Now let's understand something which is very interesting, and we call it as confusion matrix. In the next video, I'll cover in detail about the different varieties of tests which are available, Z-test, T-test, and there are a few other tests also which are non-parametric in nature, and I'll explain them in detail, don't worry. So now let's understand something called confusion matrix, which is confusing. So what is a confusion matrix? So right now, forget null alternate hypothesis for a moment. Let's concentrate only on this as a standalone scenario, and then later we'll find the relationship of confusion matrix with the hypothesis testing. So in confusion matrix, we look at the actual value and the predicted value. Okay, so we look at actual value and the predicted value. So suppose here we will consider a scenario where suppose we are trying to predict whether a particular person is likely to have diabetes or not. So in this case, if the person is diabetic, we are denoting it with 1. If the person is not diabetic, we are denoting it with 0. Okay. So suppose we have around few observations. Let's see how many I can fit in here. So we have these many observations. So let's give it some numbers because that will help us later on. So we have 9 observations. Okay. For 9 people, we have got the data. And now what we want to do is we want to make some prediction on this data. We do not know what is the actual answer. We look out for some other parameters like his blood pressure level, his height, weight, etc., etc. And we just try to make a prediction whether this person is likely to be diabetic or not. We have got some data where we already know the answer, whether the person is having diabetes or not. And before we really make some prediction on real data sets, we first want to do some testing. So in this scenario, suppose we predicted after doing some tests, what tests and what, don't worry about it right now. Suppose you did some tests and then you predicted, okay, this is 1, this is 1, this is 0, this is 1, this is 1, this is 0, this is 1, this is 0, and this is 0. So looking at the characteristic trends patterns, you have made these 9 predictions. Now, out of these 9 predictions, how many have we got right? Let's understand that. So how many are correct? This is a correct prediction. Let me use a different ink. This is a correct prediction. This is a correct prediction. This is a correct prediction. This is a correct prediction, and this is a correct prediction. And what are wrong predictions? So this is a wrong prediction, wrong, wrong, and this is also correct, right? So as you can see here, why wrong? Because the actual value is 0, which means the person was not diabetic. However, we have predicted him as diabetic. So here the actual one is 1, which means the person was diabetic, and we also predicted diabetic, fine, and these are all fine. Here, these 2 records are where the mistake has happened. This is where the mistake has happened. So here, as you can see, the actual is 1, which means the person was diabetic, but we didn't predict him to be diabetic. Here the actual person was not diabetic. However, we said that the person is diabetic. Now, in confusion matrix, we have four concepts. True positive, true negative, false positive, and false negative. So true positive means when, first of all, let me give you a shortcut on how you can remember this. So this right hand side, these positive negative ones, you always assign it to 1 and 0. So let me just put it here. So 1 is positive and 0 is negative, right? And that also makes sense, right? 1 is a positive, positive prediction, 0 is a negative prediction. So true positive means that in this case, as I said, first look out for the positive predictions we have made. Positive predictions means where we have made predictions as ones. We have predicted, right, this side. So this is what we have predicted: 1, 1, 1, 1, 1. These 5 scenarios we have predicted 1. Those are positive predictions. Now, out of these predictions, how many are true? How many correct predictions have we made? So these true or false means this T and this F means correct and wrong. Right? Now we'll answer looking at this formula. It will be much more simpler. So for the first one, let's find out how many true positives are there. So for that, first we'll figure out how many positives are there. So 1, 2, 3, 4, 5. Out of which, how many we have got right? We have got right in 1, 2, and 3. Right? So 3 of them are right. So my true positive is equal to 3. Now let's look at the ones where we made a positive prediction but that came out to be wrong. So in this case, there is called false positive. I have made a positive prediction which is false, which means this one, this record, and this record, 1 and 7. Two false positives, right? And what are the true positives? True positives are 2, 4, and 5. Now comes true negative. How many true negatives are there? Or rather, how many negatives are there at the first place? So let's look at the negative ones. So this is a negative prediction where I predicted 0. Negative prediction, negative prediction, and negative prediction. So these are the 4 negative predictions we made. Now, out of these negative predictions, how many are true? How many are correct? This is correct, this is correct, and this is correct. So, true, negative are 3. The ones are 3, 8, and 9. And what is, how many false negatives? Only one. That is row number 6. So here we have made 3 true positives, 3 true negatives, 2 false positives, and 1 false negative. So if I have to calculate the accuracy of my prediction, that will be equal to true positive plus true negative divided by true positive plus true negative plus false positive plus false negative. So here, how many true positives do we have? 3 true positives and 3 true negatives divided by 3 plus 3 plus false positive are 2, false negative are 1, which is equal to 6 by 9. If we get this in terms of percentage, 6 by 9 is around 66.67%, right? So this is all about confusion matrix. So if you have to just write one line about confusion matrix, true positives are what? I predicted true, right? I predicted, or rather, let's write something like this, something positive. It became true. True negative is I predicted something negative. It became true. False positive is I predicted something positive. It became false, right? Or rather, let me write it like this: the prediction became true. The prediction was true. And false negative is okay. So false negative is I predicted something negative and the prediction is false. All right. Now later we'll see how this can actually get connected with the hypothesis testing. Okay. So let's just take one example. Say, let's take an example of a credit card fraud. So true positive is what? So in this case, credit card fraud is 0, not fraud, 1, fraud. So true positive is I predicted fraud and it was indeed a fraud for a particular record. True negative is I predicted that it's not a fraud and it was indeed not a fraud. False positive is I predicted that it's a fraud, but it was not a fraud. And false negative is I predicted that it's not a fraud, but it's a fraud. Now, you think logically for this problem of credit card fraud, out of these four scenarios, which one is more dangerous? If we think, the most dangerous scenario in this case is false negative. Because I said it's not a fraud, it's okay, no problem with this transaction, and it turned out to be a fraud, which means the organization will lose money based on your prediction. Okay. Now, what we shall do is we'll do a quick recap of whatever we have learned so far in this session. So we have learned about null and alternate hypothesis. We have learned about confidence interval. We have learned about one-tailed and two-tailed tests, and we have learned about confusion matrix. So we have learned all these things. If you like this video, do subscribe to the channel and let me know how is it going. If you want to enroll for the course, you can click on the below mentioned link and join the wonderful journey of data science. So till then, all of you keep learning, happy learning, and I will see you soon with the next series of lectures in statistics. Thank you everyone for watching this video. Welcome friends to another exciting episode of statistics. So today what we are going to do is going to be very exciting because today we are going to solve few statistics challenges. These challenges are based on the learnings which we have acquired over the last few videos. So I assume that you have watched our last few videos, as this video is an extension of those videos. So today we will solve statistics challenges using central limit theorem, using the concepts of normal distribution, and using the concepts of hypothesis testing. So this is central limit theorem, normal distribution, hypothesis testing, and of course central tendency like mean, standard deviation. So let's get started with our challenge. So let's look at the first problem. So the problem says that batsman A scores 50 runs on an average with a standard deviation of 5. So in this case, the scores of batsman A has been compiled and it has been found that he scores 50 runs on an average and his standard deviation is 5. Now what we want to find out is what is the probability that he will score less than 40 in a given match. So he scores 50 runs on an average with a standard deviation of 5. So if for any given match we have to predict his score, or in this case we want to predict that he will score less than 40, we want to find out what is that particular probability, what are the chances. So let's get down to work. So let's first write down what are the information we have. That's very important for problem solving. So in this case, we know, so this is problem 1. We know that the mean is 50. We know that the standard deviation is 5. So now, since in this problem nothing is mentioned that what kind of distribution does the runs of the batsman is plotted against, let's assume that these 50 runs with a standard deviation of 5 follows a normal distribution. Since nothing is mentioned, let's assume that it is following a normal distribution. So let's draw a normal distribution. So this is 50. So if standard deviation is 5, then one standard deviation to the left is 45. So 2 standard deviation. So what we want to essentially find is the probability of the batsman scoring less than 40. So friends, one thing which I want to tell you is statistics is a subject which mixes numbers with intuitions. So you should not look at just dry numbers. You should always try to visualize the problem and apply a lot of intuitions. This is, by the way, not a very good normal distribution. Let me just... Yeah. So essentially, if you look at the problem is the probability of the batsman scoring less than 40. So what are we trying to find? We are essentially trying to find the region shaded in red. No, I mean, in this case, before you even apply the formulas and crunch numbers, just look at the graph. If you look at the graph, what you will see is that intuitively the chances of the batsman making less than 40 is very less, right? So it's more likely the batsman, if this is a normal distribution, the more likely is that the batsman is going to score mostly in this region, the region shaded in green here, right? Now let's find out what is the probability. So the first step, what we'll do is we'll try to find the z-score of 40. Now z-score, as you know, just a quick recap, z of x is x minus mu divided by sigma, which means 40 minus 50 divided by 5. Though intuitively we can see that it has to be minus 2, but still let's calculate. This is minus 10 by 5 equals minus 2. So now we know the z-score of 40 is minus 2. Now what we are going to do is we are going to look into the z table and find out the p-value. So this is step 2. Step 3 is use the z-score to calculate p-value. So let's come to the z table. Here we can see that the z-score is 2, which means the p-value is 0.0228. So the p-value is now what is p-value? In this case, if you remember our previous videos, p-value is the probability of picking up a random sample from this shaded region, this region, right? Which means the chances of scoring, if this is 40, the chances of scoring less than 40 in a given match is 0.0228. If I convert that in terms of probability, I just multiply this number with 100 and we will get 2.22 or 2.23%, right? So this p-value of 0.228, we can say that the chances of the batsman scoring less than 40 is 0.228 multiplied by 100. Just to calculate it in terms of percentage, it's 2.23% up to 2 places of decimal. I hope this problem is clear. Now let's just slightly tweak the problem. Suppose this is not 40, or rather this is 40. This is fine. This is 40. And suppose we want to find this place, say 39. In that case, this part is not what we are looking at. We are looking at only this part. So Z-score of 39 is 39 minus 50 divided by 5, which will be minus 11 by 5, which will be minus 2.1. So here if we come, 2.1 is 1.79%. Now if I ask you what is the probability of it scoring say greater than 40, since this part is less than 40, if I ask you what is the probability of the batsman scoring greater than 40, it's not very difficult. So 100% minus 2.23, and that is 97.77%. All right. I hope this is clear. So now let's move to the next problem. So let's look at problem number 2. So let's read the problem. You're a businessman doing grocery business. The supply of your stock is sporadic at times. Maybe you are not getting the supply from the vendors or the suppliers which supplies goods to your grocery store. You do not receive it very regularly. It's sporadic. At times you receive it on time. At times you do not receive things on time. So you even suffer losses at times if the goods are not sold within a certain period. Probably they cross expiry periods, which is very regular, especially with dairy products, right? Milk and all those stuff. If they are not sold within a certain period, you cannot sell it again because that's harmful. So you suffer losses at times and you make profits also. So profits have a mean of 2000 and a standard deviation of 1000, which very clearly shows that the business is very topsy-turvy. Though you make profits, but at times you do make losses because the standard deviation, if you look at it, it's 1000, quite high. So your team makes 100 trades per week. So you do 100 transactions. Actually, transactions will probably be the right word. So your team who is running your shop, they makes 100 transactions per week. Now, what is the probability of your team, or rather your shop in this case, because your team cannot make profit, making a loss or making a profit of more than 20,000 in a given week? So let's dissect the problem. Let's first look at what we have. So we have a population data, which is the mean of 2000 and the standard deviation of 1000. So let's write down mean of 2000 and standard deviation of 1000, right, for each transaction. So your team makes 100 transactions per week. Okay. Now the probability, what we need to find out, the probability that you make a loss and the probability that you make a profit greater than 20,000. So here, when we look at a profit of 20,000 in a given week, considering that we are making 100 trades, you can actually say that per trade, if you want to look at, it should be because this is for the entire week across all the trades. We want to find out per trade because mean and standard deviation, all of them signifies per trade. So we want to find out the probability of making a profit greater than 200. Actually, let's make the problem a bit complicated. Let's make this, say, let's make this, actually this is fine. Let's go with this. This is okay. Or let me just change these numbers a bit, maybe. So let me make this, say, profit of greater than 50,000, for example. Or rather, let's make it 5 lakhs, so that it becomes more interesting. 1, 2, 3, 4, 5. Yeah. So 5 lakhs. Or rather, let me make it 3 lakhs actually. So here now we are looking at a profit of greater than 3,000 and a loss. Loss is less than 0. So let's draw the normal distribution. So this is my mean, 2,000. This is my standard deviation, which is 1K per 1,000, just to avoid a bit of space. 2 standard deviation will be 0. And in this side, I'll just call it 3K, just to save space. So now, what do we need to find? Let's look at the problem. Probability of you making a loss, which means this particular region, and probability of you making a profit greater than 3,000, which means the region, actually let me draw profit with a good color. It's profit, so let's use green. So we want to find out the probability of a random sample being picked up from the green zone and the red zone. Eventually that's what we are trying to find, right? If I pick a random sample, what is the probability that it will be from this green zone and it will be from this red zone? Now again, as I said, First, visualize the problem intuitively. That makes life very easy. So it's intuitively very clear that the chances of you making a loss is less and the chances of you making a profit greater than 3000 is not very high, but at least it's more than you making a loss. So let's quickly crunch the numbers. So for the first problem, let's find out z is equal to 0 and we want to find this region. So loss means less than 0. That's what we wanted to find, a loss and a profit of 30,000, right? So loss is 0 minus the mean is 2000 divided by standard deviation 100, which is minus 2. And a z-score of 3000 is 3000 minus 2000 divided by, it should be 1000. So now from the z-score, let's figure out the p-values. So just to make the problem interesting, I will make a bit small changes here. I will say suppose this is 3200. Say this is 3176. So this is the reason is I just want to show you how to look at certain decimal places in z-score. So this will be 1.76. All right. So here we are looking at not this region, not greater than 3000 fully. Probably I'm looking at this region. This is 3176. And this is the shaded region. So now let's come here. Minus 2. Same 0.228. So the p-value is 228, which means less than 0 is 2.23%. Now this one is 1.76. So let's come down to the positive side. So this is 1.7
and 1.76 is this one. So 1.7 and 0.6. This is 1.7. This is 0.6. So this is the p-value when the z-score is 1.76, which means this particular region is 0.9608, which we found from here. However, we need this region because we are looking at greater than 3176. So this region is 0.9608. So this region is 0.0392. So this part is 3.92% because I am looking greater than z, and less than z is 96.08%. So let's go down. So here the p-value is, because I'm looking at this side, and the value which we get from the z table is always on the left hand side. So the p-value in this case is 1 minus 0.9608, as we are looking for greater than this 3176. Here is my 3176, right? The z-score the p-value which we get is always on the left side, but I did on the right side. I did more than greater than 3176. So in this case, this is 0.0392. So this one is 3.92%. Now from this, if you want to further derive that, if I ask you what are the chances that the shop will make profit, which means I am looking at this, and from here this should be 100 minus, let me use the same ink for calculation. So it's 100 minus 3.92%, which is 0.896. No, my bad. We should take this one, not 3.92. 100 minus 2.23. My apologies. So it should be 97.77. We are looking at this number. I hope this is clear now. So now we have solved two problems using z-score and p-value. Now let's take one step further and let's look at hypothesis testing. The steps are not going to be much different, only some small tweaks here and there. So let's start by looking at a problem of hypothesis testing. A quick recap. Before we start hypothesis testing, H0, H1, H0 is my null hypothesis, which is my anti-belief, which is something which I don't believe. H1 is my alternate hypothesis. Which is my belief, which is something more likely to happen. Right? Also, what we know is that we cannot test this directly. Because there are no statistical tests available to test the alternate hypothesis. So this can't be tested directly. So we test this, we test null hypothesis. When we test null hypothesis, we get a p-value. And what we want this p-value to be low. How much low? Ideally less than 5%. If that is the case, then we reject H0 and accept H1. So this is the high level flow of hypothesis testing, which I have already explained in deep detail. This is just to warm you up and a quick recall. So now let's start looking at the problem. So in 2015, kids were watching 26.5 hours of TV with a standard deviation of 8 hours. So in 2015, you did a survey and you found that kids were watching 26.5 hours of TV with a standard deviation of 8 hours. Since nothing is mentioned about what kind of distribution does it follow, we will assume that we are talking about normal distribution. So today, you randomly surveyed 70 kids and you found that they are watching 24.5 hours of TV. So in 2020, you randomly surveyed 70 kids. By the way, here, the word randomly surveyed is very, very important. While doing any survey, It's very important that you do it randomly. Okay? Else you can just ask your kid, their friends. That doesn't work. You have to randomly pick up 70 kids and then you have to do the survey. And you found that they are watching 24.5 hours of TV. So now the question comes is, are the kids watching less TV these days? So in 2015 they were watching 26.5 hours of TV. Probably we are talking per week average. So today in 2020, which means after 5 years, you randomly surveyed 70 kids and found that they are watching 24.5 hours, which is less than 26.5. So the question is, are the kids watching less TV these days? So here, let's break down the problem one by one. So what is the information we have? This is problem number 3. So in 2015, kids were watching 26.5 hours of TV. And standard deviation is 8 hours. So we assume that this is my population. Since we have not mentioned anything, always assume that this is my population. Now in 2020, you randomly surveyed 70 kids and you found that they are watching, these 70 kids are watching around 24.5 hours. Now mind it, you have only surveyed 70 kids. Is that enough for you to say that the kids are watching less than 26.5 hours of TV? So in this case, what we want to find out is the probability of the kids watching 26.5 hours of TV, right? Given this arrow, this vertical bar represents given, means what is when I am looking at another condition, which in this case is n is equal to 70 and x is equal to 24.5. So what do we want to find out? The probability of x being less than 26.5 when I found that n is equal to 70 and x is equal to 24.5. N is the number of kids I surveyed and x is how much TV they want. So this part I know that this is true because I have done it. I want to find out if this is true, what are the chances that this is true? We want to find. Okay. So we want to find the chances of this part being true given this particular condition. So let's go step by step. Let's first write down what is our belief. From the initial indications, our belief is that kids are watching less TV, less than 26.5 because this was my benchmark. So if you look at the problem, we are saying, are the kids watching less TV compared to this 26.5, because this was my initial population. Here I have not mentioned what are the number of kids we have surveyed, so always assume that this is the population. And any hypothesis is always done on the population, not on the sample. Like what we do is, if you think of a real life scenario, we say that the average literacy rate of, say, India is 75%, for example, right? Now suppose you randomly surveyed 100 people and you found that out of those 100 people, 90 are literate, which means the literacy rate is 90% for those 100 people, right? So you get an intuition that probably the literacy rate has increased. But is it enough? Because you have only spoken to 900 people. You have not spoken to a lot of people. But is it enough for you to make an assumption that probably it is greater than 77%, right? So in this case, you have to think like this. You have to think intuitively first. Is it enough for you, by surveying 70 kids, that the population data, which in this case is 26.5 hours, has dropped? So what is my belief? What is more likely to happen? That is my alternate hypothesis. What is least likely to happen? Now you may ask me why this is not greater. Why it is not greater or equal to 26.5? The reason behind very simple is, it's very evident that the numbers have dropped. And it's very unlikely that this will be greater than 26.5. At best, it can stay at its current position, because we can clearly see that there is a drop here. But is the drop substantial enough? Or have we spoken to enough people to make a conclusion about the population of 2020, right? That's what we want to find out. So always think that in this case, the two questions which are important is that drop enough? Is the drop enough for me to conclude that it has actually dropped? Drop enough means this and 24.5, right? Is it an enough drop? The second is, have we surveyed enough people? Right? So now let's try to solve the problem. So according to central limit theorem, what do we know? We know that mu equals to mu bar. This mu bar is the sample side. This mu is from the population side, right? So this mu bar belongs to the sample side. This I'll call the sample side. This is the population side. So according to central limit theorem, mu is equal to mu bar, which means in this case the mu bar is 26.5. The standard deviation of the sampling distribution, sigma x bar, is equal to sigma by square root of n. So sigma, as you can see, it's 8. 8 by n is 70. and that comes out to be 8.36. So 8 divided by 8.36 is 0.95. So the standard deviation is 0.95. So now let's draw this graph and let's try to mimic this condition here. Remember, this is not, I do not know whether this is true or not. I'm just trying to mimic it and see the chances of this statement being true. So this is my, according to this scenario, this is 26.5. So that's my mu bar. And my sigma x bar is 0.95. So So 26.5 minus 0.95 is 25.55, one standard deviation to the left. So this is 25.55 minus 0.95 is 24.6, which means this is two standard deviation away. And our candidate is 24.5, which is here. This part is 24.5. So now we have mimicked this in the graph. Now we have to understand one concept of rejection region. What is a rejection region? In very simple terms, rejection region is the region which does not contain 24.5 and 26.5, which means in this case this is my rejection region, the region shaded in blue, because this part does not contain 24.5 and 26.5. This region, the region on the green, that has both 26.5 and 24.5, right? This region. However, the region shaded on the blue does not have 24.5 and 26.5. So this portion is called the rejection region. Now logically, if you think, the closer these 24.5 and 26.5 come, right, that will increase the rejection region, isn't it? Like for example, suppose this is 10, is a number 10, there's a number 8, there's a number 6. So if we want to compare 8 and 10, the rejection region is higher. This is the rejection region of 8 and 10, right? Why the rejection region is higher? Because 8 and 10 are closer. The closer these 2 points are, the rejection region becomes higher, right? So in this case, it's very evident that these 2 points are not very close, which was also which is something which we also saw. This is 26.5 and this is 24.5, right? So they are not very close. What we want to find out is the coexistence of these two things. We do not know whether it's less than 26.5 or not. That's what we want to find out. When this part is true, this part is what we want to find. What is the probability, right? So the probability of this thing happening, this particular phenomenon, this particular probability happening should ideally be low, right? Should ideally be low if the rejection region is less. The rejection region, if it grows higher, then we get a higher chance of these two statements being true at the same time, isn't it? So logically think, in this case, the chances of 8 and 10, since they are closer to each other, the rejection region is higher, which means, for example, if I say that what are the chances, what are the probability of mu being 10 if I pick up a random sample which is 8, right? And the chances of mu being 10, suppose if I pick a random sample which is 6. In this case, this chance is higher because these 2 points are closer. And a closer point means a higher rejection region. The lower rejection region indicates that probably the chances will be very, very low. How much low? Let's figure out. So Z-score of 24.5, you already know, it will be 24.5 minus 26.5 divided by the standard deviation 0.95, and that is minus 2 divided by 0.95 is minus 2.10. So the Z-score is minus 2.10. So from the Z-score, I will get the p-value. I want to get the p-value of this region, and we know how to get that. So minus 2.1 is, sorry, this is the positive side. Minus 2.1 is 0.179, which means the probability of us, or the rejection region probability is 0.179, which is 1.79%. So the p-value here is 0.179, and this p-value what we get is for the rejection region, right? So now the formula is very simple from here. The p-value which we calculate, if it is less than rejection region, we can say that reject H0, right? In this case, what is my H0? My H0 is this. That is very, very, actually, you know what? This is not correct. This should be the ideal formulation. That it is 26.5, the total, actually even this is not correct. Yes. So the probability that the mean is 26.5 given that this particular thing is true, right? So the probability that this is 26.5, which means the probability of these two statements coexisting, co-occurring, and this can only be high if the rejection region is high. When the rejection region can be high? If these 2 points are closer. If these 2 points are closer, what will happen? The z-score will be lower, right? So think about this sequence one by one. So p-value is less than rejection region. I reject H0. Why? When the p-value can be less than rejection region? When the p-value can be less, actually you should know, it should not say like this. And this rejection region ideally should be 0.05. Now it's complete. So the p-value, what we calculate, if it's less than the rejection region where which should be 0.05, then we reject H0. When the p-value can be less, if the z-score is high, isn't it? When the z-score is high, if chances of two statements coexisting is high. Now what do I mean by that? Like in this case, we are looking at the coexistence of the statement that the mean of the distribution is 10, but we picked up a random sample which is 8. There are a lot of numbers. I pick up a random number, there is 8, and I know that in this case my mean is, say, so I'm looking at a distribution where mean is 10 and standard deviation is, say, 2. So I pick up a random sample which is 8, where I got 8, right? What are the chances that the probability, or what are the chances that the mean is 10? So the mean is 10 and I pick a random sample that is 8. Now this one I know is true because I have done it. What are the chances if I pick a random sample which is 8 and the probability is 10? Sorry, the mean is 10. The probability of the mean being 10 when I have picked up a random sample which is 8. That's what we want to find out. So if the z-score is, high, then this happens. If the z-score is low, then the chances, the probability of coexistence, two statements coexisting, will be low. Right? So if the z-score is low, means 2 points are far apart, the p-value will also be low because the rejection region will be low. So lower, if the 2 points are far apart, the z-score will be high, the p-value will be low, the rejection region will be low, and we can reject the null hypothesis. Right? So in this case, What p-value did we get? 0.179. So this is what we have got. That is less than 0.05. So we can reject the null hypothesis. My null hypothesis is this, which is rejected. Means the chances of this statement being true is only 1.79%, right? This one multiplied by 100 is 1.79. So this one has a chance of, this has only 1.79% chances, means this one has a chance of 98.21%, and we accept the alternate hypothesis, or rather we can say that we are 98.21% sure that people are watching less TV, but this number is so high you can actually pass it as a judgment. We can say that people are watching less TV. I hope the entire understanding of the problem is clear, because now we are going to just extend the same thing for other problems. So let me share a small tip with you. So far we have been trying to calculate the p-values, and going forward also we'll keep on doing that because that's a good practice. But let me also show you a shortcut. Do we really need to take the z-score every time? Sorry, do we really need to take the p-value from the z-score every time? I'll tell you a shortcut so that I don't even need to look at the p-value. And just by the z-score, I should be able to make a conclusion. So what is that concept? So what I want the p-value to be less than 0.05. How do I get the p-value from the z-score? Right? So now what we'll do is we'll learn a shortcut. So in order for the p-value to be less than 0.05, let's find out what is that z-score. So let's come to the z table. So let's look at a negative z table where the value, where can I find a good p-value where it is just less than 0.05. This part, this is my cutoff, so which is like minus 1.65, as you can see. This is just below 5%. So let's write down minus 1.65, and from the other side I will try to find out where exactly it is just crossing 95%. And if we see this, again 1.65, which means the rule is if the z-score lies between minus 1.65 to 1.65, you cannot reject a null hypothesis. If it's beyond this range, then you can. So if the Z-score is greater than 1.65, or if the Z-score is less than minus 1.65. If these two scenarios occur, then you can reject null hypothesis, considering that my confidence interval is 0.05. If this is 0.05, which is generally the norm. The general norm is that the confidence interval is 0.05. If that is the case, if this is the scenario, then a Z-score greater than 1.65 or a Z-score less than 1.65, I can reject the null hypothesis. Okay. Now suppose, for example, if your Z-score is, suppose I say, okay, now I want to have a confidence interval of say 0.09, which means suppose it's a very mission critical, so I want a confidence interval of 0.01, which means I want to be 99% sure of my alternate hypothesis. So in this case, the p-value has to be less than 0.01. So in that case, what we'll do is, let's look at the positive side, which means I have to find where it is just greater than 99, which is this point, 2.33. 2.33. So in this case, a Z-score greater than 2.33 or a Z-score less than minus 2.33. If either of these scenario occurs, then you can reject H0. Else we fail to reject H0. So this is a small tip which you can use. We will continue to use p-value because that gives a more intuitive understanding, but this is also a shortcut which you can follow to quickly do your calculation. Okay, so now let's look at the next problem. So if you can see, let's solve problem number 3. So average IQ of all kids, and here when I say kids, I mean all kids of the country, say is 110 with a standard deviation of 5. Fair enough. So we visited a particular school whom we are calling school A, and we randomly surveyed 50 kids within that school and found out that their IQ is 120. So what we can infer about school A kids? So what we see is that the national average is 110 with a standard deviation of 5. However, when we visited a particular school and randomly surveyed, by the way, we have to emphasize on the word randomly surveyed. We cannot survey our known people and say, okay, I'm done. We randomly picked up 50 kids and we found out that their IQ is 120. So my first impression is that probably school A kids are having a higher IQ. That's my intuition. But is it true? We'll find out. I have surveyed 50 kids. Is it enough? We'll find out. Initial impression looks like it is high. But is it really high? Let's find it out. So let's write down the problem. So for population, we have a mu or a national average of 110. Sigma is 5. As far as sample is concerned, we know that n is equal to 50 and x is equal to 120. Right? Now, if I apply central limit theorem, so mu is equal to mu bar is equal to 110 and sigma x bar is equal to sigma by square root of n. So sigma is 5 divided by square root of 50. So we'll first find the square root of 50, which is 7.07. So 5 divided by 7.07, and that is 0.7. Okay. Now what is that we want to find out? We want to find out the probability that even before finding out the probability, let's write down the important step. That is the alternate hypothesis and null hypothesis. So alternate hypothesis is that mu equals to, or rather mu is greater than 110, and alternate hypothesis is mu is equal to 110. Now I have said before, there is no point in doing less than, right? At best it can be equal. It's very unlikely that it will be less than, for these kids it will be less than 110, right? So now what we are trying to find out, we are trying to find out the probability that the average IQ of school A kids is 110, given for randomly surveyed 50 people it is 120. This is what we want to find out. And this is nothing but the probability of my null hypothesis. So now let's draw a normal distribution. So if we assume that this is 110, so 110 with the standard deviation of 0.7. So 0.7 is 110.7, then 112, right? And somewhere here it will be 120. Let me draw it a bit nicely. Right? So this is 110, this is 120, and this is my rejection region. The region which does not contain 110 and 120. Always that is my rejection region, remember it. So let's find out the z-score of 120. So z-score of 120 is 120 by 100 minus 110 divided by 0.7, and that turns out to be 10 divided by 0.7, and this number is a very large number. Very large. Which means we'll get a p-value which is very low. Which means that we can perfectly reject this and we can accept this. Okay. Now if you intuitively also see, if the new average, right, the new average should be actually not 110 but maybe 115 or maybe something else, but it cannot be 110. These 2 points are like so far ahead, away from each other, and the z-score is so large. As you can see here, the z-score will be like 10, 11, 11, 12, maybe 13, 14. Z-score will be like 14, which is a very low p-value. So we can comfortably reject this null hypothesis and accept this alternate hypothesis that there is hardly any chance that the IQ, the average IQ of the kids in the school is less than or actually equal to 110. It has to be greater than that. Let's tweak some parameters and see if we can make any difference. Suppose let's increase the standard deviation. Say the standard deviation, let's make it 20. Let's see now if it makes any difference. So in that case, this becomes 20. So 50 square root is 7.07. So 20 divided by 7.07 is 2.82. So this is does that make any difference? From the naked eye, it doesn't look like. So if this becomes 2.82, still it's not, it's like the Z-score is still very, very high. So 10 divided by 2.82 will be close to 3 point something. 2.82 is 3.54, still very, very high. Doesn't make much of a difference. Okay, now let's make some changes. Say this is not 120, say this is 115, or say 112. Now let's see if that makes any difference. Actually, let's make it 115. So in that case, this is 115. So this is 5 by 2.82. So 5 divided by 2.82 is 1.77. So this value now becomes 1.77. Now if this becomes 1.77, then let's try to figure out p-value from the Z table. So this is the Z table. So 1.77. So 1.77 will be, no, this one. So this is so 96.16. So this side is 96.16 and this side is 1 minus 0.9616, which equals to 84, which means here the p-value is slightly better, slightly respectable. We were getting absolutely no p-values at all. Very, very low p-values we are getting. So this is 3.84%. Still lower enough for me to reject the hypothesis. I hope this makes sense. Now let's look at the next problem. So the problem says, in a survey conducted 2 years back, we found that 60% of households had got tablets. Today you surveyed 200 random households and found that 68% use tablets. So what we can infer? Interesting. So today we can see on surveying 200 random households, we found that 68% is using tablets, which is higher than a survey conducted 2 years back. So we can clearly see that it's higher. But is it enough that we can say that today people are using more tablets? Let's figure out. So let's first write down the population information we have. The population information is 2 years back, 60%, right? 60%. And the standard deviation is, oh, we don't have any standard deviation. Also, the problem looks a bit new. So far, we have been dealing with whole numbers. Now we have suddenly got percentage. Neither we have any standard deviation. So we have to do something about this. First, let's convert it into decimal. And in this case, the standard deviation is 0.6 multiplied by 1 minus 0.6. So square root of mu, so the formula is mu into 1 minus mu. So which is 0.6 into 0.4. Square root is 0.48. This is my sigma. Now when we talk about sample, we have surveyed how many people? 200 households, and we found 68% are using tablet. So this is 200, and we found that 68% are using tablets. Okay. Now, according to CLT, central limit theorem, mu equals mu bar equals 0.6, and sigma x bar is equal to sigma by square root of 200. Actually, let's try to make the problem a bit interesting. Suppose this is not 6.8, say this is 6.3. That will make the problem a bit interesting. So 0.48, first let's take square root of 200, 14.14. So 0.48 divided by 14.14 is 0.03. Okay. So according to central limit theorem, we find this as 0.03. Now let's look at the null and the alternate hypothesis. So my alternate hypothesis is that mu is greater than 0.6. Very evident. Here this is 0.6, 0.63, and null is 0.6. Now what do I want to find? The probability of mu is equal to 0.6 given n equals to 200, x equals to 0.63. So now let's find out the z-score. So z-score of 0.63 is 0.63 minus 0.6 divided by 0.03. 0.63 minus 0.6 divided by 0.03, which is 1. So the z-score is 1. So now if this is 0.6, this is 0.63, and this side is my rejection region. So let's find out the z-score. 1 is 0.8413, which is this side. My rejection region is this side. So I have to do this. 1 minus 0.8413, and that is equal to 8715, which means my p-value is 0.1587, which means this one is 15.87% p-value into 100, just to take it in terms of percentage, which means, sorry boss, I can't reject I do not have enough evidence to reject the null hypothesis. I cannot accept alternate hypothesis. I do not have enough evidence to reject the null hypothesis. I cannot say that mu is not equal to 0.6, or I cannot say that mu is greater than 0.6. So that's it for today. We'll continue with few more variations of this problem. I hope you are liking this series. If you like these videos, please subscribe, comment, share. And if you want to enroll for the course, please click on the link below. Till then, happy learning. Hello everyone. Welcome to another session on statistics. So today we are going to continue where we had left off in the previous video. If you have not watched the previous video, please watch that video, because this video is an extension of the previous video. So today we are going to solve few more problems, and we are also going to learn about t-test. So far we have worked only with z-test. So we'll solve t-test problems today. We'll also look at different variations of t-test: one sample t-test, two sample t-test, and pair t-test. So let's get started. So we had solved till problem number 4. So let's pick up problem number 5. So spend a couple of minutes in reading the problem. Let's understand what the problem is. So a chair manufacturer has spent 5 million in upgrading the equipments to lower the defects in chair. So right now, when the chairs are getting manufactured, we are finding defects in those chairs. The current defect rate is 20%. So out of 100 chairs being prepared, we are finding that 20 chairs are having some defects. So the chair manufacturer spent some money, around 5 million, and he upgraded the equipments to ensure that the defect rate drops. So you are asked to develop a hypothesis that the defect rate has dropped below 18%, or rather you are asked to test a hypothesis. So the owner believes that to test Yeah, so the owner believes that his defect rate has dropped below 18%. So you are asked to test his hypothesis that it has dropped below 18%. So in order to work with it, in order to prove it, you pick up 150 random samples and found 30 defects. Now, can you use this experiment to say that the defect has lowered, or rather the defect has dropped below 18%? I think that will be the right question. Okay. So let's get started with our tried tested formulas. So first what we'll do is we'll write the population data. So we'll take mu. So mu here is, just pause the video and tell me what is mu here. On a count of 5, 4, 3, 2, 1. The correct answer is 18%. If you have thought 20%, then this 21% has been given just to confuse you. It has no relevance in the test. We really do not care about this entire statement. Our problem actually starts from here, from this part. Okay. So now we assume that mean is 18% or 0.18. Let's calculate the standard deviation. Here, by the way, this is, let mu be 18%, right? We do not know whether it is or not. So as far as the standard deviation is concerned, into 1 minus 0.18. So that gives me 0.38. So now we have got the mean and we have got the sigma. From the sample side, let's see what we have got. We have n, which is 150, and we found 30 defects. Now this mu is nothing but my defect rate. So x, or the value against which I am going to test, this should also be a defect rate. So how do I calculate the defect rate? I pick up 30 defects. We got 30 defects in 150 random samples. Okay. So 30 defects out of 150 random samples. We'll just come here in a moment. Now let's construct the null and the alternate hypothesis. So the alternate hypothesis is, So we need to test this. So this is my alternate hypothesis, that mu is below 18%. Mu is less than 0.18. And my null hypothesis is that mu is 18%, right? So let's calculate the defect rate. It will be 0.2, right? So if we get 0.2. Now let's calculate the z-score. So z-score of x is equal to x minus mu by sigma x bar. So we also need to calculate the sigma x bar. So sigma x bar is sigma by square root of n, which is equals to 0.38 by square root of 150, which is equal to 150 square root is 12.24, 0.38 divided by 12.4 is 0.03. So my critical value, sorry, my z-score is of 0.2 is x minus mu divided by 0.03. So if I calculate 0.2 minus 0.18 divided by 0.03, which is 0.67. So we got a z-score of 0.67. Now from here I have to find the p-value. So p-value is the probability that this particular statement is true. So let's find the p-value from the Z table. So this is the Z table. So our p-value is 0.67. 0.67 is here. Okay. So 0.67 is 7.7486. Okay. So if this is my distribution, this is 0.18. This is 0.2. So my rejection region is here. So what I have got is a p-value of 0.7486, which means this side is 0.7486. I need this side. So this side is 1 minus 0.7486, which is 1425. Or in another term, so this is 0.2514, which means the probability of this statement being true is around 25.14%. Now, if that is the case, I cannot reject the null hypothesis. I cannot. Right? This statement can certainly be true. Right? I cannot reject this. So, if I look at carefully into this problem, why I got such a big p-value? It must have struck you that this time the p-value is really high. Ideally, we want this p-value to be how much? To be less than 0.05. Then only I can reject the null hypothesis. But this time it's very high. How come this happened? And under what scenario this can happen? So if you carefully observe, when we had formed the null and the alternate hypothesis, here when we had done the experiment, we had found that the defect rate is 20%. However, when we formed the alternate hypothesis, we said that this is less than 18%. So that itself shows that my formulation of the hypothesis is not correct. Here I saw that it's 20%, but my hypothesis says that it's less than 18%. So these two are in stark contrast of each other. And it was expected that something like this can happen. The p-value got very, very high. So which means whenever you're constructing the null and the alternate hypothesis, you should first observe what you are trying to formulate, and you should observe the experiment properly. Right? So let's get back to the previous problems once. Like in this problem, my observation is that 68% now is using tablet out of 200 random households, and previously it was 60%. So it's evident that it has increased. And if I put a alternate hypothesis that mu is greater than 60%, I'll be fine. Right? But in this case, I clearly see that this is 0.2. But I found a hypothesis that it is less than 0.18, which is difficult to be true in any case. So in this case, my outcome is that I do not have enough evidence to reject the null hypothesis, or I do not have enough evidence against the null hypothesis. You can use any one of these statements, because the chances of the null hypothesis being true in this case is 25.14%. I hope this makes sense. So now let's move on to the next problem. So far, whatever we have seen, that all the problems we have solved are part of one-tailed test. Now, what does that mean? So if you look at our alternate hypothesis, so we had said mu less than 60%, right? Or mu greater than 110. So we have tried to solve this kind of problems. where in the alternate hypothesis, if you see that I am checking only one side, that is either greater or lesser. This is called one-tailed test. When I am checking only one side of the distribution, which can be either greater or lesser. Now, if we want to test whether something is equal or unequal, that's where we use a two-tailed test. Why it's called two-tailed? Because not equal to means it can be greater or can be lesser. So let's write down. So if you see, it is not equal to, which means it can be greater or lesser both. It can be greater than 60 or it can be lesser than 60. Unequal means that. So here it is testing both the sides. So that's why it's called two-tailed tests. Are things going to change fundamentally? Not much, apart from one minute change. So let's take a look. So let's take this problem. So you have made a new recipe in your restaurant. Okay, so you're a cook maybe, and you constantly innovate. So as part of your innovation, you have made a new recipe, and previously in your restaurant you used to have a footfall of around 60 customers on an average per day. On an average per day, I would say, with a standard deviation of 10 customers. So after you have made the recipe, you counted the number of customers over the last 5 days, and you found that you found around 400 customers over the last 5 days, which means an average footfall of 80. So has this recipe worked magic? So if I have to convert this in a two-tailed test, ideally, from this question, I would say, okay, if it is greater or lesser, but let's convert this into a two-tailed test, right? Or so has this recipe worked magic or has it bombed? So basically, we are trying to see if there has been any change after you have introduced this new recipe. So what we'll do is, let's write down the problem. So the problem is, you have a footfall of 10 customers on an average per day with a standard deviation of 10. Okay. So population data. That is the first thing you should write. Mu is equal to 60 and standard deviation is equal to 10. That is my population data. before we introduce the recipe. Now, from the sample perspective, you have x and you have n. So x is 80. Last 5 days, number of customers is 80. And n is 5. So let's write down the alternate and the null hypothesis. Let's go to the problem. So the hypothesis which we are testing is whether it has changed from 60 customers or not. So not equal to 60. Always remember, alternate hypothesis has to always deal with a change. So whenever you notice some changes, then only you want to do this hypothesis testing. And whenever you have noticed a change but you just want to confirm that statistically, that's where you end up doing hypothesis testing. So alternate hypothesis is what your belief which represents a change, and null hypothesis is something which represents a kind of a equilibrium. That means nothing has changed. So let's do the calculation. So first we'll calculate sigma x bar, which is sigma divided by square root of n. So sigma is 10 by square root of n, which is 5. So 2.23. 10 divided by 2.23 is 4.48. This is my standard deviation. So z of x is 80 minus 60 divided by 4.48. So 20 divided by 4.48 is 4.46. It's too high. I don't even need to look at anything. I don't even need to look at the p-value. A z-score of anything, if it crosses 1.6, 1.7, it's like too high. So I can confidently, and in this case what will happen is that the p-value will be too low. So if the p-value is too low, the chances of this statement occurring is going to be very, very low, which means I can reject this and I can accept the alternate hypothesis. Now let's try to make some changes to this and see how it works intuitively. Now if you think this is 80 and here like it's 60 was the previous footfall with a standard deviation of 10, and here we found 80. So what we can clearly say is that it's very obvious that something has really changed. The number, if you see the number intuitively also, it looks to be changed. Now let's take an exercise. What we'll try to do is, let's try to see how we can increase the p-value here. Which means if I have to increase the p-value, I have to decrease this z-score. Right? If I have to decrease the z-score, what are the ways in which I can decrease? One way is I can increase this. If standard deviation goes high, then automatically z-score will decrease. So let's come here. If I have to increase the standard deviation, what I can do is I have to decrease this n. If I decrease this, then standard deviation will go high. That's one way. Another way is if I increase this standard deviation, then also sigma x bar will be higher. So for example, let's say make it 20. If this is the case, then what will happen? So 20 divided by 2.23, which is square root of 5, is 8.96. Will it make a difference? So 20 divided by 8.96, it will still be, if this part is 8.96, so 20 divided by 8.96 will be 2 point something. No, still high. So still I am not convinced. So let me make it even higher. Say 30. Let's see now. Does that make a difference now? So 30 divided by square root of 5. Let's try this one. 13.45. Yeah, now I think we should get something meaningful. So this part will be 13.45, which means so 20 divided by 13.45 is 1.48. So if that is the case, let's see. So z-score is 1.48. Okay. So now the p-value does not, I don't think it will be too low. So 1.48. So let's first draw the diagram. So this is my mu, which is 60. This is 80. And this part is my rejection region. So if I go and find out 1.48, so 1.48 is 0.5. 93, which is this side. So if I have to calculate the other side, this is 1.1 minus 0.93, which means 0.07. That's my p-value. Now, for a two-tailed test, so far what we have seen is that for one-tailed test, the p-value has to be less than 0.05. In this case, this is slightly higher. So anyways, I cannot reject the null hypothesis. But for a two-tailed test, this is a change. It is not 0.05 anymore. Because now I am testing two sides, greater as well as lesser, which represents inequality. Right? So this 0.05, which I was getting for one-tailed, where I was only testing either greater or lesser. Now this 0.05 is going to be get divided by 2, because this will, both of them will take or stake claim in this 0.05. Previously it was only being taken by greater or lesser. So here this is not equal, which means both greater and lesser, and both of them will take a pi on this 0.05. If that happens, then what will happen is for each of them, like this one is 0.05, fine, no problem. Both of them combined is 0.05, but each of them will get 0.025. Which means when I'm getting the rejection region, I'm only getting it from one side. So whatever we are getting from 0.07, this is not sufficient for this. It's only testing greater side. But I also need to check the other side. So in this case, my p-value will be this into 2, which means it will be 0.14. So we can clearly see that I cannot reject the null hypothesis here. So let's make some quick changes. So let's bring down the sigma, maybe make it 25. Just to now check if I can, I want to now reduce the p-value slightly, and I want to reject the null hypothesis. So if this is 25, so 25 divided by 2.23 is 11.2. Divided by 11.2 is 1.78. If that is the case, let's find out the p-value. So 1.78, p-value is 0.9625. So let's write down 9625. So 1 minus so 3.75 is this one. So in this case 0.03.75 into 2 will be my p-value. So no, it's still we are not able to reject. So what I have to do is I have to reduce this slightly more. So if I say make it 22, I think we should be able to do that trick. So 22 divided by 2.23 is 9.86. So this is now 9.86. So 20 divided by 9.86 is 2.02. So our Z-score is 2.02. So 2.02 is 0.9783. And now I can clearly say that yes, we can reject it. Why? Because now if you look at carefully, whenever I'm calculating one side, right, I want one side to be actually less than 0.25, right? Then only if what is my ultimate objective? My ultimate objective is to get a p-value of 0.05 for both greater and lesser, which means each side is getting 0.25, sorry, 0.025 actually. So each side is getting 0.025, which means this is my cutoff, because this side is 0.97, and if I have to get a p-value of 0.025, then I have to cut at this point, which means 1.96 is my cutoff. If my Z-score goes beyond 1.96, then I can reject the null hypothesis. So for a two-tailed test, the shortcut is a Z-score if the Z-score is between this range, then you can not reject H0 or null hypothesis. Okay, and if the Z-score is greater than 1.96 or lesser than minus 1.96, then you can reject the null hypothesis. So now let's quickly do one more problem, our last problem in Z-test, just to recap our concepts. After this, we'll move on to T-test. So your restaurant has got red interiors and the customers were spending before 5,700 with a standard deviation of 3,000. Fair enough. Now you have changed the color. So from red, probably maybe you have done green or blue, whatever. Now you believe that the customer spend will also vary with it. So you randomly surveyed the spend by 300 customers and you found that their average spend is 6,000 rupees. So now the question which we need to answer is, did this change of interiors or did this change of colors, did it have any impact, rather any significant impact in spending by the customer? So let's write down the problem from our population. We have mu, which is 5,700. We have sigma, which is equal to 3,000. And here we have sample. So I have x, I have n. So this is 300 and my x is 6,000. Now let's write down the null and the alternate hypothesis. So the null hypothesis is that mu not equal to 6,000, sorry, not equal to 5,700. And here mu is equal to 5,700. Now let's calculate sigma x bar. Sigma x bar is sigma by square root of n, which is 3,000 by square root of 300. This is 17.32. So 3,000 divided by 17.32 is 173.21. Now let's calculate the zx, which in this case is x minus mu by sigma x bar, which is equal to 6,000 minus 5,700 divided by 173.21. So we get a z-score of 1.73. So if we see here, it is falling in between, which means I cannot reject the null hypothesis. I'll say, sorry, I do not have enough evidence to say that the spending has changed. So I cannot reject this. Now, if I have to increase the Z-score, here, notice that I have not even looked at the p-value. In case I have to, let's do that as well. So this is 5,700. Yes, 6,000. And this is one of the rejection regions. The other is on this side, but I'll not calculate there. I'll rather find it here and then multiply it. So Z-score of 1.73 is 0.9582. There is the other side. This side is 0.9582. So this side will be 1 minus 0.9582, which is equal to 0. So my p-value is 0.0418 into 2, which is 3608, which means the chances of this being true is 8.36%. So that's why I cannot reject the null hypothesis, because this has to be less than 5% for me to reject it. So let's try to just make some changes and try to see if I can make it reject. At what value? So ideally this has to be greater than 1.96. So if I have to increase the Z-score, I can probably increase this value by a bit. See if I make this 6,500. So in that case, this will be 6,500. So 500 by 1.73. So 500 divided by 173.21 is 2.88. A Z-score of 2.88. If I come here, 2.88 should be this one, I guess. Yes, 0.9999.8. Okay, so this is if that is the case, then this is 200, which means even if I multiply it by 2, it's not going to be very high. So in that case, I can reject. So this is it from Z test. Now we'll continue with or start T test. Okay, so now let's start exploring T test. So let's look at T test. So t-test is a mini version of z-test. It works like z-test but with some differences. So all the conditions which we have done so far, which we have satisfied so far, the concept of null hypothesis, alternate hypothesis, concept of Z-score, concept of central limit theorem, to a very large extent they apply to t-test as well. Of course there are some tweaks. So as I said, t-test is a mini version of z-test. So when do we use t-test? So we use t-test when number one, normal distribution, the underlying distribution is normal. In one of the later lecture series, I will give you a brief overview on what test to use when and what are the conditions. So just now know that t-test works with normal distribution. The same is also applicable for z-test, by the way. So both z-test and t-test work on normal distribution. Here the metric in consideration is mean. So metric in consideration, so we'll be working with mean. There are some non-parametric tests where we will consider median, which will, as I said, show in the later videos. So here metric in consideration is mean. In t-test we do when generally the number of samples is less than 30, and number 4, when the population standard deviation is unknown. Is not known, right? However, rest of the concepts are more or less the same. Here also we'll try to calculate something called a t-statistics, the way we were calculating the z-score, and then we will be looking at the p-value, though in a different way. We'll be looking at a critical value and we'll be comparing the calculated value and the critical value, and then we'll make decisions whether we should accept or reject the null hypothesis. So let's look at a problem. Okay, before that, let me also mention the varieties of t-test available. So the main varieties of t-test are one sample t-test, two sample t-test, pair t-test. So let's look at each of these problem one by one. So let's read problem number 8. So let's read the problem first. So it is recommended to walk 10,000 steps per day to be healthy. So when you walk more, you reduce obesity, and that's good for health. And the doctors have prescribed to walk 10,000 steps per day. And these days, as you know, there are a lot of apps, wearables through which you can track how many number of steps are you taking per day. So you randomly surveyed 10 people and found that they are taking these many number of steps respectively. So when we look at this particular data, it's like very evident that these people are taking less than 10,000 steps, most of them. Yes, there are some exceptions, but most of them are taking less than 10,000 steps. But can you use this data to infer about the entire population? Can you use the samples which you have taken for 10 people to infer about the entire population and say that the entire population is taking less than 10,000 steps? That is the problem. So here, first things first. So this is a one sample t-test, because what we want to test is if the sample mean, which means sample mean is coming from here. These are the samples which we have taken. If this mean is statistically different from a hypothesized mean. Here, this is not an exact mean. This is not my population mean. This is the hypothesized population mean, right? This is not the exact mean. I do not know, right? How many steps people are taking. We have hypothesized that people are taking these many number of steps, and we want to compare the mean of this group, the mean of samples, versus this hypothesized mean. So this is my hypothesized mean. So looking at these two numbers, can I say that these mean of samples, whatever we are getting, right? And here, mind it, we have worked with only 10 people. And looking at this, can we infer the same about everyone in the population? That's the problem. So let's try to solve it. But before we try to solve it, one question which might be striking you, that it's actually looks very simple, which means if I have to do a survey, I just need 10 people, which means I can talk to my father, I can talk to my mother, I can talk to my sister, I can talk to a couple of friends, couple of colleagues, couple of neighbors. I can collect that data and then infer the same about the entire population. It's actually simple. Why does statisticians take so much of pain in gathering so much of data? It's just 10 people whom we need to talk, and we know more than 10 people, right? That might be coming in your mind. Now, one thing which you need to remember is that these 10 people are randomly surveyed 10 people, which means that it cannot be biased. You cannot say, okay, I am going to pick this person, this person, this person. I know that they are like taking 10,000 steps or less than 10,000 steps. I speak to them, I form my hypothesis, I do the testing, and I can give a result. No, because they are not randomly surveyed. You know about them and you are picking up their information. That's not random survey. Random survey means you do not know about that person. Suppose you go stand in front of the road, you just randomly ask people. And that also cannot be from a particular state only or a particular city only. Then you will lose diversification. So it looks very simple that I just talk to 10 people and my work is done. That is not the case. Okay. So now let's try to solve this problem. Let's first see what information do we have in our hand, and then let's try to solve it. So the first information which we have in our hand is a hypothesized population mean. So just for simplification, I say this is my population data. Though this is a hypothesized mean, this is not the real mean. So this is 10,000. So now we'll find sigma. So we come to the problem. We are trying to find a hypothesized sigma, but hold on. This is hypothesized mean. This is not my population data. And in this case, I don't have a standard deviation. And if you remember, I use t-test when my standard deviation of the population is not known. Fair enough. So I do not know this. Let me just put a cross. This is not x, this is a cross. Next thing what we'll do is, we will form a alternate hypothesis and a null hypothesis. So my null hypothesis is that it's less than 10,000. My alternate hypothesis is that it is equal to 10,000. Now, I do not know the standard deviation. So, this is my sample site. So, let's write down whatever we have. So, we have a mu bar. Which is equal to mu, which is equal to 10,000. Then sigma x bar is equal to sigma by square root of n. But unfortunately, in this case, we cannot do this because there is no sigma. I do not know the sigma. Okay, fair enough. Let's look at n, which is equals to 10. And we also need a critical value, which we can call as x. Which is also something which we do not have. So let's try to figure these things out one by one. So let's test. So here I have pasted all these numbers. So all the numbers I have copy pasted, and then I am calculating the mean and the standard deviation. As you can see, the mean is 8595 and the standard deviation is 1428.36. So here from the sample I can calculate the standard deviation. I do not need the population standard deviation. So it's possible for me to calculate the standard deviation. So my standard deviation is 1428.36 and the mean is 8595, which is nothing but this x. So if you remember during Z test, right? If you remember during Z test, this used to be our x, the average in the in the sample side. Here also used to compare it against this average in the sample side. Here we do not have it directly, but we can certainly calculate it from here. So we have the standard deviation and the mean. Either they will be mentioned explicitly, or you can be given data like this and you can calculate the mean and the standard deviation. Now for t test, we'll calculate something called a t statistic. So the funda is the same, x minus mu bar divided by standard deviation by degrees of freedom. I'll just explain you in a moment what is degrees of freedom, and you get a square root here. Okay, so we'll just pause here and let's just quickly understand what is degrees of freedom. Again, a common mistake which I see between people is they say degrees of freedom is n minus 1, where n is the number of samples or the population size. That is not correct. In most of the scenarios, it is n minus 1, but let's understand the concept. Suppose I have 4 numbers. Suppose they are 4, 4, 3 and question mark. Now what I tell you is, I tell you that their average is say 5. Now looking at these details, can you calculate this particular missing number? The answer is yes, we can, and the answer will be 9. So as you can see, knowledge about these 3 numbers was enough for me to derive the 4th number, as long as I know the average or some metric. Average actually works in most of the scenarios. So in this case, out of 4, knowledge about 3 variables or 3 observations is good enough for me. So in this case, my degrees of freedom is n minus 1. For this particular data, it's n minus 1, where n is the total number of samples. However, is it always n minus 1? Let's take a scenario. Suppose I say I have 4 numbers, 4 4 question mark, and I tell you that the average is 5, and I also tell you that suppose this is 1 2 3 4. I also tell you that number 3 is equal to number 4. If I tell you these two things, can you calculate these two numbers? The answer is yes, we can. And in this case, the answers are 6, 6. Looking at these two scenarios, right? The answer is 6, 6. So here in this case, as you can see, the degrees of freedom is n minus 2. So not necessarily that it has to be n minus 1. That's the message which you need to take over or take home. Most of the scenarios it will be n minus 1, but not necessary. Here it's n minus 2 because knowledge of n minus 2 variables was good enough for me to derive the next numbers when I know this particular condition. Okay, so now we understand all of these things. Let's just plug the numbers. So x is 8595 minus mu is 10,000 divided by 1428.36, which is my standard deviation, divided by degrees of freedom, square root of degrees of freedom, which means here my n is 10, so 10 minus 1, and that comes to, so let's first calculate the denominator. 1428.36 divided by 3 is 476.12. So this is the denominator, 476.12. Now let's come to the numerator. 8595 minus 10,000 is minus 1405. That divided by 476.1, and we get minus 2.95. So this is my t statistic, and we'll going forward we'll call it as t calculated. You can call it as t calculated. Also, you can call it as t statistic. It's very similar to our Z-score. Now, let's find out something called a critical value. So here we have the t table. Now, since this is a one-tailed test, here as you can see, this side is the degrees of freedom. So let's look at the critical value for a one-tailed test. So here my degrees of freedom is 9. So I'll come here, and this is the critical value for degrees of freedom is equal to 9. for a one-tailed test with a significance level of 0.05. So this is my critical value for degrees of freedom 9, significance level 0.05, being it a one-tailed test. So let's note down this value, 1.833. Okay. So my T calculated, we had found it to be minus 2.9, and T critical is 1.833. So if we just draw the curve, suppose this is my mean, and this is my threshold, which is, since here the way the T table is constructed, it does not take care of the negative values. So whenever we get a positive value, in case we have to work with a negative value, in case here since T calculated is negative, what we'll do is we'll put a negative value here. So this part is my, or this point is my T crit. Now the significance of T crit is that T calculated should be between mu and T crit. T crit is the maximum point beyond which I'll reject the null hypothesis. So here, if my T calculated is here, anywhere here, between here and here, if I can find a T calculated say here, then I cannot reject the null hypothesis. If it goes on this side, then I can reject the null hypothesis. This is my cutoff. The moment it crosses this cutoff, you can reject the null hypothesis. So that is the significance of the critical value. It's a cutoff, it's a threshold. So in our case, let's see where we find our value. So this is our T calculated. So as you can see, T calculated is beyond T critical. So in this case, the thumb rule which we will follow is, if T calculated is less than T critical, then reject H0. So in my case, H1 was that mu is less than 10,000 and H0 that H0 is mu is equal to 10,000. So in this case, I can comfortably reject the null hypothesis and I can accept the alternate hypothesis. So here I reject the null hypothesis that people are walking 10,000 steps, that hypothesis is rejected, and the hypothesis that people are walking less than 10,000 steps, that particular hypothesis is accepted. So here my hypothesized mean is this, and as you have seen here, so we see that yes, the sample mean which we calculated from here is statistically different from my hypothesized mean. Okay, in this case it's less because it's very evident that they're taking less than 10,000 steps. Now we'll look at a two sample t-test. So this test is significant when we are trying to test the difference between two population means. So let's read the problem. So we have visited two schools. In school A, we randomly surveyed around 30 kids and found that their average IQ is 110 with a standard deviation of 5. In school B, we randomly surveyed 20 kids and found that their average IQ is 115 with a standard deviation of 10. So now we can test the hypothesis that the IQ between the kids in the two schools are not equal. So I have, as you can see here, we test the difference between two population means. So here my two populations are school A and school B. And in school A, I have randomly surveyed 30 kids and I have noted down their average IQ and the standard deviation. I have done the same in school B, where I have randomly surveyed 20 kids and noted their average IQ along with the standard deviation. Now I have to test the hypothesis. The IQ between the kids in the two schools are not equal. So in this case, let's do a two sample t-test. So as you can see here, my null hypothesis is that mu A equals to mu B. Mu A is for school A or group A. Here as you can see, we have two schools. H1 is that the mean are not equal. Now how do I calculate the t statistics or the t calculated? The formula is this. So we take the mean of group A, in this case which is school A. We take the mean of B, in this case which is school B. We take the standard deviation and then we have the number of observations with which we are dealing. So let's just plug it and see what we have. So in school A, we spoke to 30 kids. In school B, we spoke to 20 kids. In school A, the average is 110 with a standard deviation of 5. In school B, it is 115 with a standard deviation of 10. So now let's calculate this step by step. First, I have calculated the numerator, which is mu A minus mu B. So 110 minus 115, that is 5 or minus 5. Then denominator 1 is nothing but this part. This is deno 1. This is deno 2. Then I'll add them and then I take the square root. So I've done it step by step. So we have calculated numerator. This is the numerator. So denominator 1 is 0.83 sigma square divided by n1. So sigma square, as you can see, I have taken standard deviation square, which is b4, and divided by b2, which is nothing but n1. Similarly, denominator 2, c4 is nothing but my standard deviation square divided by c2, which is the total number of kids we have surveyed. Then I have added these two, which is this part, this addition. Then I have taken the square root, and then I have calculated t statistics, which is nothing but numerator divided by the denominator, and we find that t statistics of minus 2.07. So this is my calculated value. Now what is my critical value? If I do a say a two-tail test, then my critical value will be this two-tail test with 0.5 as my p-value, or 95% confidence, whatever you want to say. Here let's see how many records we have actually. So here we are dealing with, here for my bigger case it is n is equal to 30, and here it's n is equal to 20. So in this case both are different. So let's pick n is equal to 20. So here if I look at it, the p-value or the critical value is 2.086 if I pick n is equal to 20. Okay, so this is 2.086, this value for n is equal to 20, critical value of 0.05, and I am doing a two-tail test. So let's take this value. So my critical value is 2.08, and I will put a negative sign, and as we can see that it's like very close, and the t statistics is inside is less than the t critical value. So if I had to draw a graph, if this is my mu and this is my t critical, and this is where my t calculated is, very close. It's like neck to neck. So in this case, I do not have enough evidence to reject the null hypothesis. In this case, I cannot reject the null hypothesis. I hope this is clear. So now we'll move to the last test as far as t-test is concerned, and that is a pair t-test. So we use this test when we are interested in the difference between two variables for the same subject separated by time. Suppose you have studied the score of few students, or say in this case one student, I would say score of a student, pre and post joining a course. Assuming that here the data is normal and here also the data is normal, both pre-course and post-course. The question is, do you observe any statistical difference between the scores of the student after joining the course? Which means, did joining the course help the student or not? So here we are looking at the same subject. The same subject is the student, separated by time, pre-course and post-course, and we are interested in the difference between the two variables. So let's put these values in Excel. So here I have put these values in Excel, and the way to calculate the t-test is, first we'll calculate the difference, which is this part. We'll calculate the difference square, which we require here, and then the rest is straightforward. So here what we have done is numerator minus 33, which is nothing but difference. Then denominator 1 is 2457. Let's see what do we have for denominator 1. So denominator 1 is nothing but n, which is this, which is nothing but the count, multiplied by summation of d square. So here what we'll do is, so multiplied by summation of d square, which we have got from here, the difference square, minus summation of d square, which is this part. So I take the summation of difference, which is something which I've got here. Then I want to subtract this minus this. So denominator 1 minus denominator 2, and I get this value. Now denominator 3 is this entire expression, the numerator versus the denominator. The numerator in this case is this value. This is my numerator, and this part is my denominator. And then finally I take the square root. After that I calculate the t statistics divided by numerator and denominator. So that gives me my t statistic. And here for degrees of freedom 9, we have already seen that the value is 1.833 for one tail test. For two tail test, let's figure out what is the value. This is the value, for 0.05, 2.26, and the value which we have got is 2.52, so slightly off, which means I can reject the alternate hypothesis, reject the null hypothesis and accept the alternate hypothesis. So that's about paired t-test, where we are pairing for a same subject attributes which are separated over time, pre-test and post-test. The substitute of this test, this paired t-test, we are assuming that this distribution is normal. If this is not normal, then the substitute of this test we'll learn in the later videos. We have something called a Wilcoxon test. So we'll learn about it in the next video. So I hope you have been able to grasp Z-test, T-test, hypothesis testing, the formulas, and we have solved 10 problems. So if you like the videos, please like, comment, share, subscribe. If you want to enroll in the course, please click on the link below. So I will be back with a new video where I will be discussing few other tests very soon. Till then, happy learning. Hello. Welcome to another session on statistics. So I hope you are liking the statistics series. If you have not watched the previous videos, please go back and watch the previous videos once. Because today's lecture, today's session is a continuation of the previous lectures. So I strongly recommend you to watch these recordings, these sessions in sequence, as all of them are connected with each other. So today we are going to start with a small, I would say, description, a small table which we will try to build, where we will try to show what kind of tests to be applied when. So there are a lot of hypothesis tests. So we'll look at what kind of tests to be applied when, and then we'll also look at few of the tests. So let's start writing hypothesis test here. What we already know is that hypothesis test is where we test a hypothesis which we call as an alternate hypothesis, and we try to form a null hypothesis. Then we try to find out the probability of the null hypothesis, and if the probability of the null hypothesis is low, we reject the null hypothesis and we accept the alternate hypothesis. Second scenario is we may not have enough evidence to reject the null hypothesis. So let's look at the hypothesis tests which can be done. So first division is between continuous data and here we have categorical data. So when it comes to categorical data, we use a chi-square test, which we will see in one of our lectures, maybe in this lecture as well. And then we have continuous data. So within continuous data, we have normal distribution, continuous data which follows a normal distribution, and non-normal distribution. So there are certain tests which only works with normal distribution and certain tests which works with non-normal distribution. So let's look at these tests, and here within normal distribution we can further subdivide this test. Actually, let's do it in the next slide. So we'll continue with this thread. This thread will look at normal and non-normal. So let's start with normal distribution. So within normal distribution, if we want to test with mean, or if you want to test with variance, that decides what kind of test we actually want to use. So if we are testing with mean, then we have some tests. If we are testing with variance, then we have some test. So the test with mean are Z-test, which we have extensively done in our previous videos, T-test, which also we have extensively covered in our previous videos. So if you have not watched them, please go ahead and watch. Then we have ANOVA, which we will cover. When it comes to variance, we have something called an F-test. We'll have a test called Berlet's chi-square. We are not going to cover this test, at least in these videos. They are not much used, because when we are dealing with normal distribution, mean generally suffices. Now when we deal with normal distribution, as I said, mean tests generally suffices. Now let's look at non-normal distribution, which is this side. So we have covered this, we have looked at this. Now non-normal distribution, if we look at it, so here we deal with not mean but median, right? And that's makes a lot of sense, because non-normal distribution, the data is going to be skewed left, skewed right. So mean may not be the right matrix to deal with. So we deal with median, and we also have some test with variance. So here, if we want to test for variance, we use something called a Leven's test, which we are going to see. And the other scenario is if we want to test with median. So if you want to test with median, we have tests like sign test, then we have Wilcoxon, then we have Whitney. So Wilcoxon and Whitney we are certainly going to discuss. And there are a couple of other tests as well. So one is called Kruskal-Wallis. So it's called Kruskal-Wallis. We are not going to discuss this test, but just good to know. Then we have a test called Moods median. This is all for when we want to test with respect to median. And last but not the least, if we want to test with median, we can also do a Friedman test, or I would say Friedman test. So a quick recap. From hypothesis test, we can do it on continuous data, we can do it on categorical data. Within continuous data, we can have normal distribution, we can have non-normal distribution. For normal distribution, if you want to test with respect to mean, then we can do these three tests. If you want to test with variance, then we want to do these tests. For non-normal data, if you want to test with median, then we can do sign test, Wilcoxon, Mann, Whitney, Kruskal-Wallis, Moore's median, Friedman. For variance, we do Levin's test. Now you may ask, okay, why so many tests for median? Because they are tested, these tests are useful under certain scenarios with some other conditions as well. It's not only mean or median. Like in this case, as you remember in the last session I had said, that there are certain scenarios where we can do Z-test, there are certain scenarios where we can do T-test, and there are certain scenarios where we can do ANOVA. However, all of them are related to mean. Okay, so though we are testing for mean, but still these tests work for different purposes. The purpose is very, very different. So having said that, let's start the series of tests which we are going to discuss. So a quick recap on Z-test and T-test. So Z-test is used when the number of samples are greater than 30, when the population distribution is normal. And how do I know whether the population distribution is normal? We'll use something called a Shapiro test, which we'll see. Number 3, when the population standard deviation and the population mean are known. And number 4, when the observations are independent of each other. So in order to do a Z-test, these 4 prerequisites must be met. What are the prerequisites for a T-test? Population should be normally distributed. For that, we'll use Shapiro test, which we'll see now. The variances should be comparable. For that, we use Levin's test. And yes, you're right. It's the same Levin's test which we are talking about. So we'll see what this means. And number of samples are less than 30. If these 3 scenarios are met, then we can do a T-test. We can also do a T-test in case population mean and standard deviation are known or can be derived. For Z-test, we cannot do a Z-test if the population standard deviation is not given. Right? Even if the number of samples are greater than 30, but if the population standard deviation is not known to us, you cannot do a Z-test. So now let's take our hands at a Shapiro test. So we are going to remove everything and we are going to do it from scratch. So let's start. So now we have Shapiro test. So here what we want to do is we want to find out whether the weight of apples in grams, what we are seeing, do they follow a normal distribution or not. As we have seen, normal distribution is a must-have prerequisite for both Z-test and T-test. So now we are going to check how to actually ascertain, how to determine if a particular distribution is normal or not normal. So here we have taken weight of apple in grams. So here I have sorted them in ascending order. So first let's look at it in a crude way, which we have done it previously as well. Just a quick recap. So what we are first going to do is we are going to calculate the standard deviation, as you can see, for all these 55 samples. And then we are also going to calculate the mean. So we have a total observation of 55 and we have standard deviation and mean. Now, in order to adhere to normal distribution, between one standard deviation to the left of mean and one standard deviation to the right of mean, we should have 68.2% of the data. So out of 55 records, 68.2 is 37.5. So between 13.53 and 20.97, we should ideally have 37.5 records. In this case, this has to be a whole number. So let's say take 38. So 38 records should be between this range. In our case, we find that 13.51 is this to 20.97. If we go, it's up to this. And we find 35 records, which we see here. Now between two standard deviation to the left and right of mean, that's what we have done. Two standard deviation to the left of mean and two standard deviation to the right of mean. If that is the case, we expect 52.5747. And if I take an absolute value of this, oh, sorry, absolute value will not give me the whole number. I was trying to find the whole number. Absolute value will only remove the signs. So it doesn't matter. That's fine. So here 52.47, which approximates to 52. In our case, we have 54 records. So 9.81, this first record gets excluded. And then from 9.41 to 24.69, here in this case, it stops in 23.9. So we expected around 52 records, we got 54. And between three standard deviations, 6.09 to 28.41, we expected 55 records and we have got 55 records. Fair enough. Now, can I say that this distribution is normal? Here we can see that there is slight variation. But is it okay if I say that the distribution is normal or not normal? So for that, we are going to run a test called Shapiro test. So let's run this Shapiro test. So now what we are going to do is, we are going to copy these comma separated values and we are going to calculate the Shapiro test. So first let's look at the histogram. If I look at it, it looks more or less like a normal distribution only. More or less. So now let's decode this slowly and steadily. Here we have got the mean, we have got the standard deviation, we have got the variance, we have got the kurtosis, all are okay. Now let's understand these three particular statistics in detail. Okay. So now what we are going to do is, let's understand these things in a bit more detail. So let's come here. So first, since this is a hypothesis test, what we are going to do is, we are going to form the null hypothesis and alternate hypothesis. So as I have said before, null hypothesis indicates stability. So it says data is normally distributed. Alternate hypothesis is that the data is not normally distributed, which is a state of some change, right? So whenever we observe change, we test that hypothesis, we form an alternate hypothesis and we test that hypothesis. So here my null hypothesis is that the data is normally distributed. My alternate hypothesis is that the data is not normally distributed. So for Shapiro test, we use something called a W statistic, and the formula is that we get a W calculated, which we calculate from the data, and we get a W critical, which is a standard value. So for other subsequent tests, we are going to do this calculation by hand. So all the subsequent tests will follow this same formula, calculated and critical, calculated and critical. Okay. So we want to calculate this by ourselves, and this critical value is as per the standard. In this case, the tool has done the calculated for us. So the tool has done the calculation for us, and the calculation is 0.97. So I'll copy this. Calculated Shapiro-Wilk statistic W, that is 0.97. Here the tool has already calculated it for us. So this is 0.97. And then what is the critical value? The critical value is 0.95. Right? So the critical value is 0.95 and the calculated value is 0.97. Okay. So what is this critical? What does this critical value means? That if I have to get a p-value of 0.05, what should be this value? I repeat, if had my p-value been 0.05, what would have been this value? Now, according to this formula, here it says if wcal greater than wcrit, then we cannot reject H0. If wcal is less than wcrit, then we can reject H0 and accept H1. So in this case, my wcal is greater than wcrit. So we cannot reject H0. We do not have enough evidence against the null hypothesis. If we want to be 95% sure for our alternate hypothesis, we cannot do that, because the chances of the null hypothesis being true here is more than 5% for sure, because the p-value should have been the critical value for p-value is equal to 0.05 is 0.95. If the calculated value was less than this, then I would have said that the p-value will be less or equal to 0.05. If the calculated value was 0.05, 0.95, I would have said that the chances of the null hypothesis being true is 5% and this is 95%. This is my critical value for my p-value to be 5%. But in this case, it is certainly more. Ideally, it should have been less. But if that is not the case, then we do not have enough evidence to reject the H0. What is my H0? That the data is normally distributed. I cannot say that the data is not normally distributed, at least from here. Okay, I do not have enough evidence to say that the data is not normally distributed. So probably I'll tend to believe that the data is normally distributed. Right? Now what I want to understand is that what is this actual p-value? Here we calculated again 0.05 and we saw that the calculated value is 0.97. But if it is 0.97, right, then what is the p-value? That I do not know yet. I just know that this is greater than 0.05 for sure. But what is that exact value? That I do not know. So let's try to figure that out from this calculator. So from this calculator, it's the same thing actually. So if we just put this value once more and calculate this test, right? So here, from here we can try to test the p-value. Let's try to calculate the p-value. So in our case, the W is 0.97 and number of samples is 55. So the p-value is 0.18. That means there is at least 18% chances. So here the p-value is 0.18. So in this case, I will tend to believe that it is normally distributed. It is having 18% chance, which is not very high, but certainly I cannot say that the data is not normally distributed. That is for sure. I have enough evidence against this fact. This is 82%, right? But I have to be at least 95% sure. And I am 82%, which is way less than 95%, right? So there's a fair enough chance that the data is normally distributed. And we also saw that. We saw that it's not perfectly normal, but like there's a fair enough chance, right? So there's an 18% chance of this data being normally distributed, and there's 82% chance that this data is not normally distributed. But in order to pass as a judgment that the data is not normally distributed, this is definitely we cannot say that for sure. Okay, so we can take this assumption and we can say that probably I'll somewhat lean towards the null hypothesis, because this is way less than 95%. Okay, very less, right? So this certainly cannot be true. That is for sure. So that's how we test normality of a distribution. This is something which we have done before. Just a recap: if the distribution is not normal, you can use log transformation, feature scaling, Boxcox transformation to turn a non-normal distribution into a normal distribution, though it does not work always. Feature scaling does not work always. In fact, in most of the scenarios, it will not work. So mainly, we use Boxcox transformation to turn a non-normal distribution into a normal distribution. Feature scaling is something which we will take a look at it later, but this is a footnote which we need to understand. Okay, now we'll go to the next test called the Levin's test. So it's a test of equal for equal variance. So between two distribution, if I want to check if the variance is comparable or not, that's where we use the Levin's test. So here we have two groups, right? So group 1 and group 2. Now what we want to find, the variance which group 1 has. Does group 2 have got the same level of variance? Like for example, suppose for example in country A, okay, I calculate the variance between the people for education, suppose for education, or actually not education, let's do income. Right? So if I take the variance between income in country A, so this is what I want to find out, and I want to take country B, their variance in income. Can I compare these two? Are these comparable? Which means, suppose for country A, rich is say at 10, suppose an index 10, and poor is at an index 2, which means my gap is 8. In country B, suppose rich is at 15 and poor is at say 6, which means that the gap is 9. And I can say these 9 and these 8, they are like very close. The variances are comparable. The variation within country A and the variation within country B are comparable. That's where we use Levin's test. So let's look at this test. Here in group 1 we have got 9 samples. In group 2 we have got 8 samples. But that's perfectly fine. It doesn't need to be the same. I just want to understand the variance, that the variation which group 1 has and the variation which group 2 has, are they comparable? So step 1, I am going to calculate their mean. I am going to calculate their average. So as you can see, this is the average for group 1. And this is the average for group 2. So now what we are going to do is, we are going to calculate the variance. So how to calculate the variance? So group 1, so each individual observation of group 1 minus the group 1 mean, and we'll square it up. So for this case, I take this minus this and then I square it up. Then I take this minus this and I square it up. So these are the numbers which we have got for the first one, for the second one, and so on. So as you can see here from the formula, this minus this and square it up. This minus this and square it up. This minus this and square it up. Right? For each observation, I am subtracting the mean, I am squaring it up. Now I do it for all the records for group 1, and I similarly do all the records for group 2. So for group 1, I am done. For group 2, I am done. Very good. Now what we will calculate is the degrees of freedom for group 1 and group 2. So we have calculated that. This is n minus 1. And here this is also n minus 1. So we have calculated the degrees of freedom of group 1 and group 2. Now we are going to calculate the variance. So the variance is this sum divided by the degrees of freedom. Here we are working with some samples, so we take degrees of freedom. And in fact, in Levin's test, you have to use degrees of freedom. And here we calculate variance, this sum, where we have calculated the sum by taking the difference between two data points, the individual data point and the mean, then squaring them up, then adding them up, and that gives you the variance when I divide it by the degrees of freedom. Now what we are going to do is, we are going to divide the bigger variance by the smaller variance. And if I do that, so this is 17.94 divided by 17.07. and this is 1.05. Just by the intuitive look of things, we think that they are related. They looks to be related, right? The variances looks to be equal because the closer the F statistics is to 1, the better it is, right? The closer the F statistics is to 1, the better it is. That means the two groups are comparable. Now we are going to look at the F table. So we'll open the F table. So here is our F table. And now, as I had told you, that we have to look at into the degrees of freedom of the numerator and the denominator. Right? That's why we were calculating it, because that's required. So in this case, degrees of freedom is of the numerator, which is the bigger variance, which is this one, which is this one, is 8, and the smaller one is 7. So numerator is 8, because the bigger variance is the numerator, and in this case the bigger variance is this one, group 1. So it's 8 and group 2 is 7. So 8, 7. So this is 8 and this is 7. So 8 will be this one. And this is 7. And if I go right up, I will see 8 is the second right. Yes, second from the right. So what we have done is correct only. Now we are going to look at the critical value for a p-value of 0.05 for the null hypothesis. So if the null hypothesis had to be true, right? The critical value, what is the critical value for null hypothesis? When the null hypothesis does not need to be true, sorry. If the null hypothesis has to have a p-value of 0.5%, then the critical value is 3.73, not 0.5%, sorry, again, it's 0.05 or 5%. So the critical value is 3.73. So let's take 3.73. That's my critical value. So here my critical value, which I found from the F table, is 3.73. And my calculated value is 1.405. So let me just remove all these things. We'll do it fresh. So my critical value is 3.73 and my calculated value is 1.05. Now what we are going to do is, we are going to look into this formula, and what we see is that the critical value is greater than the calculated value. If that is the case, then we cannot reject H0. What is my H0? So the variance of two groups are equal. And what is my H1? Variances of two groups are not equal. So in this case, I cannot accept this hypothesis, because for that to be true, my calculated value should have been greater than the critical value. If that was the case, then only I could have rejected it. But in this case, I do not have enough evidence to reject it, which is all good. But I'm curious to know what is the exact p-value for this 1.05. I want to know that. Right? I know that it is certainly much greater than 0.05, because that, if you see the difference, is certainly greater than 0.05, but what is the exact value? This one I cannot accept, this one I cannot reject, but I'm still curious to know what is the probability of this statement being true. So let's do that. Let's pick up this test, this online Levin's calculator. We'll pick it up. and we'll try to see and derive the p-value. P-value belongs to the null hypothesis, as you already know. So here my degrees of freedom of one is 8 and the other is 7, we know it. And we are calculating against 0.05. And we saw that it's 3.73, which we have already seen before. Now what I'll do is, I'll try to play with the probability value and see if I can get close to 1.05. What is that p-value which takes me close to 1.05? So if it is 1, it is 2.75. So I still need to reduce. I'm still quite far off, say 0.2. 1.93, which means the p-value will certainly be more than 20% or 0.2. So let's make it 0.3. 1.51, in our case it's 1.05. So we still need to do more, say 0.35. 1.35, no, I am at 1.05. As you can see, my calculated value is 1.05. I want to find out the exact critical value, sorry, the exact p-value. So let's keep going, say 0.4. 1.22, which means okay, we still need to go further, say 0.5. 1.01, so it has to be between 0.4 and 0.5. So in this case, this is 1.05 and this is 1.01, right? And which means I have now gone below that critical value. So now I have to go back, say 0.46 or 0.45. Let's start with that. 1.11, okay, let's go slightly higher. 0.48 is 1.05, which means here my p-value is 0.48. Okay, that means the chances of this statement being true is 48%, which is a good enough number. For me, for a null hypothesis, this is a good enough number. So we certainly cannot reject this. The chances of this statement being true is 52%, right? So the chances of the null hypothesis being true is 48%, which is a good enough chance because it's as simple as, tossing a coin. When we toss a coin, the chances of a head is 50% and the chances of tail is 50%. So in this case, what are the chances of the variance, that the variance of two groups being equal? As high as the chances of getting a tail when you toss a coin. So it's quite high, right? So we have looked at Levin's test, we have looked at Shapiro test, and we have also understood what test to apply where. We have looked at the conditions, the prerequisites of Z test and T test. Now we will look at some other non-parametric tests, which are Wilcoxon test and Mann-Whitney test. So we'll now look at Wilcoxon and Mann-Whitney test. If you come here, it's a non-normal test. We test it when the distribution is non-normal and we want to test for medians. So we are going to look at these two tests now, Wilcoxon and Mann-Whitney. Okay, so let's start on Mann-Whitney and Wilcoxon test. So as I have mentioned before, these tests are non-parametric in nature, and mainly they are using median as the evaluation parameter. So what is a non-parametric test? So a non-parametric test is a test where the test can be applied to any kind of distribution. So far we have looked at Z-test and T-test, which can only be applied for normal distribution. So let's look at Mann-Whitney and Wilcoxon test and the difference between those tests. So we have completed up to Levin. So let's look at Wilcoxon test. So Wilcoxon test is used if the population distribution is not normal. But does that mean that it can't be used when the population distribution is normal? It can be used. But generally, when the population distribution is normal, we use Z-test or T-test. It is called a non-parametric test, which means that it does not depend on the underlying distribution, whether it's normal or not normal. So when it's normal, we use Z-test or T-test. When it's not normal, we use Wilcoxon and Mann-Whitney. But having said that, Wilcoxon or Mann-Whitney tests are generally used if the distribution is not normal. Third assumption is that the observations have to be ordinal, which means the observations which we are going to use as part of our experiment, that have to maintain some order. Fourthly, and most important, that Wilcoxon tests are done on the same group before and after an event. So, for example, I want to build a drug, and I want to apply the drug on a human being before, or rather, what I want is, I want to measure the impact of drug on the height of an individual. So I will measure take their measurements of few individuals before applying the drug and after applying the drug. However, that does not work with Wilcoxon. Wilcoxon is always on the same group. So generally, a same person undergoing multiple experiments, right? Like for example, let me give you an example. So here we are looking at the performance of students before joining a tutorial and after joining a tutorial. So we have recorded the marks of the students across 13 subjects. As I said, it has to be in the same group. A common mistake what I see is people apply this test on different groups. That cannot work with Wilcoxon. For that we have a different test. So here it's on the same group, but before and after a certain event. So here, who is the group? Group is my student 1. He is the focal point in this case. So we want to measure his metrics before and after an event. What is the event here? During the tutorial. So, and after joining the tutorial. So before joining the tutorial and after joining the tutorial, we have recorded the marks. Now what we want to find out? What we want to find out is, has there been any significant difference in the score of student 1 after joining the tutorial? Right? Can we observe any difference which we can call as statistically significant? So here are the scores before joining the tutorial and after joining the tutorial. So on a naked eye, what we can see is mostly the scores have increased. But Is it statistically significant enough for me to say that yes, probably the tutorial is having an impact? So let's find out. So it's a very simple test actually. The calculation is not very complex. So first step, what we are going to do is we are going to calculate the difference for each line item. In this case, these subjects. So here for each line item, we calculate the difference. So as you can see, we have calculated the difference before and after. So after minus before is what we have done. And we have seen that in these two cases, in these three cases rather, it's negative. Rest are all positive. So in these cases, we have seen that the marks of the student has increased. In these subjects, the marks of the students has decreased. So the next step, what we are going to do is we are going to calculate the absolute difference. So here, as you can see, we have a sign, but now we are getting rid of the sign. We are taking the absolute difference. So this is the absolute difference. So in the next step, so here, as you can see, this is the difference and this is the absolute difference. Now what we are going to do is we are going to create a rank. So as you can see, the lowest one is 0.1 as far as absolute difference is concerned. So we have given it a rank 1. Then 1 is a difference where we have given it a rank 2. 1.2 is rank 3. Difference of 2 is rank 4. 2.2 is rank 5. 3.1 is rank 6. 5.3 is rank 7, and so on. Now, in the next step, what we are going to do is we are going to identify where the difference was negative and we are going to add their rank. So as you can see here, we have added the rank where the difference was negative. And we also add the rank where the difference is positive. So from here, it's positive. As you can see that the sum is 75. And here, this is 75 and this is 16. 16 is the 3 negative ones. Now what we are going to do is we are going to take a minimum value of these two. So the minimum value, as you can see, it's 16. So we are going to take that and we are going to call it as W calculated. So here is my formula. So I have put W calculated as 16. Now, so let's remove this because let's keep that as a suspense. Let's also remove this. Okay. So now we are going to find the critical value. So let's look at a critical value from the Wilcoxon sign rank test. So here, what are my number of observations? It's 13. So am I doing a one-tailed or a two-tailed test? So let's start with a two-tailed test. So if it's a two-tailed test, then the critical value for alpha is equal to 0.5 is 17. So for alpha is equal to, so critical value is 17 for two-tailed test. So we just want to know whether there is a difference or not, right? So now we are going to follow this formula. What does this formula says? If W calculated is greater than W critical, in that case we cannot reject H0. Which means there is not enough evidence to reject, or there is not enough evidence against the null hypothesis. However, if W calculated is less than W critical or equal to, then we can reject H0 and accept H1. So in our case, this is true. So W calculated is 16. And W critical is 17. So we can reject H0 and accept H1. Now what is H0 and H1 here? A0, as you can see, it's a state of equilibrium. So which in this case is that median 1 is equal to median 2. What is H1? Median 1 is not equal to median 2. That means the performance of the student has changed after joining the tutorial. So here we are doing a two-tailed test to start with, right? So what we'll also do is that we will look at an online calculator and see how that behaves for Wilcoxon. So this is a test. It's a two-tailed test. We are starting with a two-tailed test. And the significance level we have kept at 0.05. So we have kept the values before and after. And let's calculate. Let's see what do we find. So what we find is that the p-value is equal to 0.039, which means only 3.98% chances are there that the null hypothesis is true. So the chances of this incident to be true is 3.98%. That is less than 5%. So which means we can reject this hypothesis and we can accept this hypothesis. Now let's make some changes. So what we'll do is, say, let's make some changes to the score. Say I make it as, say, 14. Say this one is 12. I'm just trying to bring the scores closer, or say 12.5 rather. Say this is 18. So I have made some changes to the score. Does it make any difference in this case? So let's also make this as 8.5. Okay. So we have made some changes to the score. Let's do a couple more. Okay. So now we have made certain changes to the score. So let's see the impact of that. So I'll copy this entire thing from here and I'll paste it here. Now let's mark all the yellow ones where I have negative difference. Any other negative differences? Okay, I actually need to copy this as well. All right. So here is one more, and here is one more. So we have taken all the negative differences. Now we have converted them into absolute differences. Now let's try to do the ranking. So we have to be very careful here so that we do not make any mistake. So this is 1. This is 2. This is 3. This is 4. This will be 5. 6. This should be 7. 8. 9. 10. No. This should be 9. 10. 11. No, I'm again making mistakes. So let's do it. After 5.6. Oh, there's a 4.6 also here. See, this is very confusing. So 1 is this, 2 is this, this is 3, this is fine, 4, 5, 6 is fine, 7 is fine, this will not be 8. This will be 8. This will be 9, 10, 11, 12, 13. So now I think it's correct. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Fine. So here we have got the sum of positive negative differences as 19 and positive as 72. So let's do 19 and 72. Now we can see that we cannot reject H0. We have come into this zone now. We cannot reject H0. And if I want to know that what is the exact probability for null hypothesis, so what we can do is, let's try to copy this and try to paste it here. So this is before. And this is after. So now let's do the calculation and see what do we find. See, as you can see, H0 is accepted. Why? See the probability. 14.65%. Though I have hesitance to say that we'll accept H0 until the p-value is very high, I think the safer bet is to say that we do not have enough evidence to reject H0. So in this case, my H0 is 14.65, which means my chances that this statement is true is 14.65, which means there has not been any change in the performance of the student. Now, if I have to do a one-tail test on the same thing, say I'll say median 2 is greater than median 1, right? So if I have to do that, so what I'll do is I'll just make it a one-tail test. Let's say do before and after. It's obvious that it cannot be before, cannot be greater than. At least from this data set, we cannot say that before is greater than. Actually, I have given before greater than after, so it should be before less than after. Yeah, at least on a naked eye, we see that the after one is better. But is it good enough to say that it's statistically significant? Let's see. In that case, what is the p-value? Around 7%, around 7.32% chances that, right? Around 7.32% chances that we can not reject H0. And as you can see, the larger the p-value, the more it supports H0, because p-value always represents H0, which I have been telling throughout my lectures. Okay, so here the chances are that 7.3% chances are there that it has increased, or rather it has not increased, it has stayed the same even after joining the tutorial. Okay, so not only you should look into this table, at the same time you should also look at these online calculators just to find out what is the exact p-value, and that will make the subject even more interesting. Else just doing this calculation from here, putting in this formula, it's not a big deal. The fun starts when you start exploring and understanding what are the chances of the null hypothesis being true. So if you have followed my previous lectures, previous series, even this particular video, you have seen that I always stress on also finding the p-value. That makes it very, very interesting. Okay. So in this case, if median 2 is greater than median 1, the performance of the student has increased after joining the tutorial. That's the interpretation. But has it actually increased? Statistically, we cannot say that. We have to be at least 95% sure. In this case, we'll be probably 85.35% sure. So the chances of this statement occurring is 85.35%. Right? Okay. So now what we will do is we'll look at another test. And this test is called the Mann-Whitney test. So here again, this is used if the distribution is not normal, the observations has to be ordinal. This is applicable to independent samples. This is called non-parametric because it does not depend on the underlying distribution. But what is the most important point is that the tests are done on two different groups. In Wilcoxon, we saw that the subject was one. I mean, subject, not the study subject, the experiment subject was student 1, which was the same subject, right? Here, the experiment subject will be two different groups. So let's take an example of Mann-Whitney. Suppose here we have two movies. So movie A and movie B. And whatever you see on the these numbers, these are nothing but the ratings of the movie. So movie A has got certain ratings by the critics. Movie B has got certain ratings by the critics. Now, what we are going to do? We are going to create an ordered list. In the ordered list, what we are going to do? We are going to take the ratings from both the movies and put it here. And then we have ordered it. So first we took the ratings from both the movies and then we have ordered it. So here what is my objective? My objective is to find whether there is any significant difference between the ratings of these two movies or not. If we are doing a two-tailed test. For one-tailed test, we'll see again greater or lesser. But we want to prove things statistically. Is it statistically significant that movie A and movie B have got different ratings? They're different in nature, right? And here, as you can see, intentionally what I have done is I have made one less observation in movie 2, which means it's not mandatory that the number of observations has to be same. So this is done by purpose to show you that this test absolutely works even if the number of samples in the distributions are not equal. So here we have created the rank and we have ordered the list. So now what we are going to do is, as you can see, in a lot of cases, there has been a tie. I can see 1, 2. Actually, I think we need to order this. So what we'll do is, let's pick this one. Let's do it from scratch. Let's pick this one. Let's pick this one. So I will not consider this. It's fine. Put the borders. Now let's try to order this. Oh, I think it was correct only. So, oh yes, this was correct only. We had 3 2s. Sorry, my bad. Everything was correct. So here we have 3 2's. So all these 3 2's are coming at the top. So 1, 2, and 3. Then we have 2 3's, which are here. Then we have a 4. So this is the 4. We have 2 5's. We have 2 6. And then we have 7, 8, and 9. So this is my ordered list. Now, what I have done is here, as you can see, these colors signify something. What we see is that all the 3 numbers are 2, but the rank is 1, 2, 3. Here again, both the numbers are 3, but the rank is 4 and 5, which is not correct, right? So I can tell you that what used to happen in my school days is that whenever we used to get same marks, since my name is Suvajit, it was like S was way behind in the alphabet, right? So any guys who are having names starting with A or B or C, right, D, in spite of having the same marks, my roll number was used to be behind. And when we used to study, the roll numbers, at least in my school, the roll number was based on the marks you get on the previous class. So a lot of times, in spite of scoring the same marks, just my name started with a different alphabet, an alphabet which comes later in the series. So my roll number was a bit behind in spite of getting the same marks. So here the same thing has happened. And this is not correct. This is not fair. So what we have done here is, as you can see, this is my initial rank, which is same as this. Then what we have done is we have created an updated rank. And how we have created this updated rank? So we have taken the average of these 3 ranks. So average of 1, 2, and 3 is 2, which we have put here. Average of 4 and 5 is 4.5, put here. Average of 7 and 8, here we are a tie here, so that is 7.5. Average of 9 and 10 is 9.5. So now we have made sure that there is no injustice. So we have created an updated rank. So now let's see what we can do with this updated rank. It's very simple. Now we go back to the original distribution and we plug these updated ranks. We plug these updated ranks against the movie ratings. Once that is done, we take a sum of these ranks. Sum of rank for movie A, sum of rank for movie B. Then we do something which we called as calculating mu statistic. So if you see, mu statistic is the rank sum minus n into n plus 1 divided by 2. What is n? The number of observations. So we'll do it for both the groups. So as you can see here, this is rank sum. Rank sum is B9 minus n, which is this count, into n plus 1 divided by 2. And here we have done the same thing. B9, which is the rank sum, minus n into n plus 1 by 2. And then we take the minimum of these 2 values, which is 5.5. So as you can see here, I have put this in the formula as well. So everything gets automatically calculated. So now let's come back to the calculation. So here we have got 5.5 as mu calculated. Now let's look at mu critical. So here is the Whitney table. So we'll get the critical values for here for our two-tailed tests. So now what we'll do is, let's try to figure out this N1 and N2. And as you can see, there it can be different. So here in this case, my N1 is 7 because I have 7 observations. Here my N2 is 6 because I have 6 observations. So my N1 is 7 and N2 is 6, which means 7 and 6 intersects at these two rows. So the critical value at 0.5 confidence interval, or alpha, not the confidence interval directly, I'll check alpha at 0.05 is 6. So now let's take that and see. So the critical value is 6. And as you can see here, if mu calculated is less or equal to mu critical, then we can reject H0 and accept H1. And if mu calculated is greater than mu critical, then we cannot reject H0 because we do not have enough evidence to reject, or we do not have enough evidence against the null hypothesis. So as you can see here, the hypotheses are that rank 1 is equal to rank 2, which means the distribution is same, which means the movies are same basically, they come from the same distribution. And H1, the alternate hypothesis is that the rank 1 is not equal to rank 2, which means the distribution are not same. So in this case, we have found that we can reject this theory and accept this theory. So if I want to know the exact p-value, which I always recommend you to do, because that makes the subject interesting. So here we have values from both the groups. We are looking at a two-tailed test at a significance level of 0.05. Everything is fine. Let's calculate. So what do we find? 3.05% chances of the null hypothesis being true. Okay? And as you can see, the smaller the p-value, the more it supports the H1, because p-value always belongs to H0 or my null hypothesis. Now, if I start to make some changes here, say for example, I make it 6. I'm just trying to make it closer to the original data. Now let's see what does it come. Now I expect it to be, I mean, we will not be able to reject the null hypothesis so easily. So here we have crossed the barrier, 5.86%. So the chances are that now we cannot reject the null hypothesis with at least 95% confidence. Let's try to bring them even more closer. Say, I'll try to increase this more. Let's try to see. Now what we see is something very interesting. The p-value has become very high, 94.16, which means 94.16% chances that the two movies are coming from the same distribution, right? Or maybe two movies are same, or the ratings are actually collected from the same distribution, or maybe if I just want to distinguish whether movie 1 and movie 2 are actually the same movie coming from the same distribution, you can think of various interpretations of that. But what we see is the p-value has become very, very high, right? So that's it on Mann-Whitney test. Now the last test for this lecture we will see for ANOVA. So the full form of ANOVA is analysis of variance. So now what we are going to do is, it's a different kind of test. So let's open ANOVA. So as you can see here, we have 3 movies and 4 critics, 3 columns and 2 rows. So far what we have seen is that we are comparing the same subject across 2 groups or maybe 2 different distributions. But with ANOVA, we see that there are 3 distributions, not 2. Moreover, ANOVA deals with variance. So far we have been mainly dealing with mean and median. So what does the basic premise of ANOVA? As we can see, there are 3 distributions. So whenever there is a distribution, they will have some variance. So movie 1 is going to have a bit of variance, movie 2 is going to have a bit of variance, movie 3 is going to have a bit of variance. So the point which we want to prove is the variance of movie 1, the variance of movie 2, the variance of movie 3, are they comparable or not? If the variances across the movie are more or less the same, right? Then in that case, what we can see is that probably the variance is not coming from this side of the data. The variance is probably coming from this side. Let's understand this intuitively. So here there can be 2 scenarios. One is that the critics are very different, which means they're for the same movie they're giving different kind of scores. Like this is movie 1, but suppose for example critic 1 gave 3, critic 2 gave 9, critic 3 gave 5, critic 4 gave 8. So what we see is that there's a huge discrepancy in the way that critics are giving the scores. Like for example, for this movie again, critic 1 gave say 4, critic 2 gave 8, critic 3 gave say 6 maybe, critic 4 gets 7.5. So as we can see, for the same movie, the scores by the critics are very different. Third scenario, say third movie, say critic gave 3.5, here critic gave 8, here he gave 7, he gave say 6.5. So here what we see is that the variance in the data is coming from the fact that the critics are very different. For the same movie, the scores are very, very different. However, when we look across the columns, we do not see much of a difference. So a particular critic have more or less given similar kind of ratings for 3 movies, which means the difference, the variation in the data, the total variation in the data can be attributed from this part, not from this part. So we call it as between or within. So this part is my within and this part is my between. So between the movies or within the critics. You have to think like that. Within is the row, the variance in the row, between is the variance within the column. So in this case, let's do the calculation. So we have to calculate 3 things. Sum of squares within, which is within the rows, sum of squares total, the total variance, and sum of squares between, that means between the columns. So how to calculate sum of squares within? So this is the sum of group mean minus each element square. So here, this is the group mean for movie 1, group mean for movie 2, group mean for movie 3. So now what I'm going to do, I'm going to take each individual observation and then subtract it from the group mean, square it up, and then keep on adding them. So as you can see here, for each group, for this group, we are taking this value, subtracting it from this, squaring it up, then adding. Then we'll again do it for this, with this. We'll keep on subtracting, squaring, and then adding all of them together. And that will give me sum of squares within, across the rows. Then sum of squares total is sum of grand mean minus each element square. What is grand mean? Grand mean is nothing but mean of all group means. So if I take all these 3 group means, I get a grand mean. Now from grand mean, I am going to take each observation, subtract it, square it, and then keep on adding it. So I'm going to have 12 additions. 12, subtract, square, and add. So as you can see here, we have 12 expressions. So that will give me sum of squares total. Now what is sum of squares between? Sum of squares total minus sum of squares within. And as you can see, sum of squares between is very, very low, which is expected because there is hardly any variance between them. But sum of squares within is very, very high. In fact, out of the total variance, it's all coming from within part, not the between part. So here, as we can see, between is very, very low. So now how to calculate ANOVA? So here we have to calculate something called an F statistics. So we have calculated SSB, sum of squares between. We have calculated SSW, sum of squares within. And as we can see, the formula is right here. So let me just squeeze it slightly so that you can see the formula while we do the calculation. I'll bring it here. Maybe here, yeah. So this should be fine. Right. So N is number of groups. How many groups are there? There is the number of columns is 3. N is number of elements within each group. How many rows? 4. M minus 1 and N minus 1, because as you can see in the formula, we need M minus 1 and N minus 1. So that is 2 and 3. Now we have to calculate the numerator and the denominator, and then we'll get the F statistic. So the numerator is 0.02. How is it calculated? Sum of squares between divided by M minus 1. So sum of squares between divided by M minus 1. Then F stat denominator, sum of squares within divided by M into N minus 1. So as you can see, M into N minus 1. So that gives me denominator. If statistic is numerator by denominator, which we get as 0.004. Very, very low. So now let's make some changes to the data and let's see how it behaves. So now let's try to create kind of a balance in the data. So let's say try to create some difference between the movies here. So without doing any calculation, we can clearly say that there is no statistical difference, or there is the difference between the columns is absolutely not statistically significant. The value is very, very low, and the contribution is coming all from within, not from between. Now let's try to create some gaps within. So suppose movie 1 for critic 1, so he has given 5 here, maybe say 2.5 here, and say 8 here. Critic 2, say for the same movie, say 6, 7.5, or rather say 3 and say 7. Predict say 9, 6 is fine, or rather let me say this is 7, this is 4. So I'm just trying to create differences between the movies. So this is 7.5. And then last but not the least, so this is 6, this is 5.5, and this is say 9. Now we can see that the sum of squares between is high. Fair enough, but is it high enough for me to say that sum of squares between is there? So let's find it out. So this F stat which we have calculated is 16.27. So let's come here and plug it. So calculated is 16.27. Now we have to find the critical value. So we can find it from the F table. So degrees of freedom in the numerator and degrees of freedom in the denominator. So in the numerator, my degrees of freedom is 2, denominator is 3. So 2 and 3, which means this is 2, this is 3, and this is where I need to pinpoint. Now with 0.5 as the p-value, this is my critical value, 9.55. So let's just plug it in. So this is 9.55 at 95% confidence. Now let's see what is my H0 and H1. H0 is state of equilibrium. Mean 1 is equal to mean 2 is equal to mean 3, which means the variance between the groups is not more, but the groups are like very similar in nature. And the difference is coming from within the rows. And H1 is mean is not equal to mean 2 and not equal to mean 3, which means the variance of the between the groups is more, or the groups are not similar. And this can be ANOVA works when we have 3 or more groups to compare. It's not only 3, it can be even more. So now let's just plug the values. So this is 16.27, and the critical value is 9.55. We can reject H0 and accept H1. So what is my H0? This is my H0 which can be rejected. And this is my H1 which can be accepted. So variance between the groups is more. We accept this theory and reject this theory. Okay. So that is it from ANOVA. So we have learned a lot of tests, and with this we are going to complete the set of hypothesis test. Now we are in the next series we are going to look at correlation, covariance, and chi-square, which tests the relationship between categorical and continuous variables. If you have liked our videos, the prior videos, as well as if you like this current video, please like, share, subscribe, spread the word. We have tried to make it as intuitive as possible and as easy as possible. If you like it, please share the word. If you want to enroll for the course, you can just click on the link below, and then we'll be happy to have you in the course and discuss, learn, discover a lot of new topics. So statistics is the base for data science, and you have to get this right in order to make a career in data science. So thank you for watching this video, and I'll see you in another series. Till then, happy learning.
And that's a wrap on part 3. A huge congratulations for completing these 10 hours. You've just mastered the normal distribution, a cornerstone of statistics. You're now equipped with not only identity and understand this fundamental distribution, but also to apply it to real world data and make powerful statistical inferences using concepts like central limit theorem and z-scores. But the journey is just getting started. The skills you've gained are perfect setup for your next exciting phase, building predictive models with machine learning. So in part 4, we'll delve into machine learning, covering linear regression, decision trees, and random forests to create powerful models that drive real-world impact. You are doing phenomenal work, and the best is yet to come. To stay on track for part 4, hit that subscribe button and turn on notifications. Thank you for watching till the end, and I'll see you in the next part.